Welcome to this second course in this specialization on math for machine learning and data science. In this second course, you learn about calculus. So derivatives, what does that mean? How does it work? How is this used in machine learning? And you also learn about some advanced techniques like Newton's method. I'm thrilled that once again we have as our instructor for this course, Luis Serrano.
Thank you very much. Yes, I'm very excited about this course. Machine learning is a lot of minimizing and maximizing functions, and that's the main application of this course, and for that we use derivatives.
In fact, almost everything we do in machine learning, certainly a large fraction of what we do in machine learning, is create a cost function and then minimize it, and that's calculus.
Exactly. When you want to train a machine learning model, you calculate how bad it is with the error and try to minimize that. And so for that we use derivatives, we use gradients, and we teach a lot of techniques.
Yeah, so often those, few lines of code implementing gradient descent or some other algorithm, that is actually using calculus that someone had derived a derivative and then implementing that in code. So understanding that seems central to having good intuitions about how the algorithms are doing.
Absolutely, yeah. If you want to understand how these optimizers work, that they normally look at black box, if you want to understand them, it's good to know the calculus behind. And at the end of the day, you're just doing something step by step, right? Because gradient descent is just taking small steps to get lower and lower and lower values. And in what direction do you take that step? Well, the gradient tells you exactly the direction.
So one thing that sometimes seems mysterious to people learning this for the first time is when you think about derivatives in one dimension or two dimensions, that's like the slope. But in machine learning, we often take derivatives in very, very high dimensions, like a 10,000 or a million dimensional space is really hard to visualize. So in this course, you also give people intuitions about what's going on in these very high dimensional spaces and when you do calculus in these very high dimensional spaces.
Absolutely. So just like you saw in course 1, data can be very high dimensional. And when you talk about the derivative, it could be in many directions. And these are captured by long vectors and long matrices. So we even go for like second derivative. A second derivative would tell you what the curvature of the space is based on the matrix that comes out of the second derivative.
And the derivative of derivative, that also leads into the Newton's method.
Yeah, Newton's method is a really cool method to minimize functions. So gradient descent actually works well, but many times gradient descent could take hundreds of steps, and Newton's method could take just a few steps to get the same results.
Yeah, doesn't work for all applications. Many ones with not too many parameters, but when it works, it can be blazingly fast.
Yes, and the idea is for you to have a toolkit of different techniques, and if this one works, that's fantastic, but if not, you try this one or that one or that one, and that's how we do it in machine learning, right?
And in fact, in terms of toolkits, one of the cool things about this specialization is also all the notebooks, all the labs.
Absolutely. So just like in the previous course, you'll be able to have a lot of code labs where you can see this concept working in real time.
So in this course, you learn the concepts, run code labs, and hopefully even come away with code snippets that you can use in your own projects. So I'm excited to have you dive into this second course and start learning these important concepts of calculus. So with that, please go on to the next video.
Let's talk quickly about programming experience. This course is designed to both provide you a theoretical background in the mathematics underlying machine learning and show you how those concepts are applied in practice. That means you'll need to do some programming. This course includes graded programming assignments and ungraded programming labs that focus on the application of the skills and concepts you're learning. These exercises are written in Python and will appear as Jupyter Notebooks, an interactive web-based interface that allows you to read, run, and edit those programs. You won't need to be an expert Python programmer to be successful in the exercises, but you should be comfortable with the concepts that would typically be taught in an introductory Python programming course. This includes things like different data types and data structures, control flow using conditional statements, loops, and functions, as well as importing and using different Python libraries. You should be comfortable reading and editing Python code using these concepts, writing and debugging your own code, and occasionally referring to the documentation of new packages. If you are a confident programmer in another programming language, you should be just fine learning the Python you need for this course as you go. If you're new to programming, however, I would recommend you take an introductory Python course before you begin this course. In the next reading item, you will find some great resources for where to get started learning Python. Welcome to week 1. In this week, you're going to learn the intuition behind the concept of the derivative. What's a derivative? Well, my favorite example of a derivative is velocity. So the first example you're going to learn is a speedometer example. Then you're going to see several very important and very basic functions in mathematics, such as a constant function, linear functions, quadratics, polynomials, exponential functions, and logarithmic functions. And you're going to learn the derivative of those functions. Now, in order to find derivatives of more complicated functions, we're going to use several rules, such as the sum rule, the product rule, the chain rule, and multiplication by scalars. But here's a question. Why are derivatives and calculus so important in machine learning? And one of these reasons is that derivatives are used to optimize functions, in particular, to maximize them and minimize them. That means finding the maximum value or the minimum value of a function. And this is very important in machine learning. The reason is that when you want to find the model that fits your data in the best possible way, you do this by calculating a loss function and minimizing it. So we're going to see several examples of minimizing functions. The first example is going to use an example of temperature. And then we're going to see other examples that actually will introduce you to two of the most important loss functions in machine learning, the square loss and the log loss. So let's begin by considering this problem. You have the following houses. Each one has a different number of bedrooms. The first one has 1 bedroom and the second one has 2 bedrooms. Now, the first house costs $150,000 and the second one $250,000. And in this problem, you would like to be able to predict the price of a house using the number of bedrooms it has. So luckily, you have a lot more data about the pricing of a house given the number of bedrooms, as is shown on this table. See, in this table, you have houses with 1, 2, 3, 5, 6, 7, 8, and 10 bedrooms with their prices. And then there is this 9-bedroom house that is still missing its price. So you decide to build a machine learning model to help you predict the price of the house with 9 bedrooms. Now, to make this easier, let's plot the data. In the following graph, the horizontal axis represents the number of bedrooms and the vertical axis the price of the house. And you can see that the houses are here represented by dots. Now, the idea is that the machine learning model takes in all the input data of the house prices and begins a process called model training. You can think of this phase of model training as the most important part of running a car, the engine. Model training is what's under the hood of any AI experiment. And in this case, in fact, it's a smart engine, always looking for ways to optimize in order to produce the best possible result. So when I say model, in this case, what I mean is simply a line that goes as close as possible to all the points. And this line would represent the predicted price. So when model training begins, it starts with any random line. And the idea is that it tweaks the results in order to optimize the best possible prediction for the existing data points. And once training is done, the model is able to give you a good prediction for the house with 9 bedrooms. So in this case, the house with 9 bedrooms is predicted to have a price of $950,000. This problem is called a linear regression problem. Now, how does training work under the hood? Well, you'll find out soon enough. But let's actually consider another example. Let's say that you travel to a distant planet and you're lucky enough to meet some alien life. And you're able to interact with them. So the first alien says the following, "Ak, ak, ak." And let's say that you have enough information to know that this alien is in a happy mood. Then let's say that another alien says beep, beep. And you know that this alien is sad. And let's have more data points. An alien says ak, beep, ak, and that alien is happy. And then it says ak, beep, 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 and it's sad. So the idea is that you don't necessarily want to learn the alien language because it may be too hard, but you want to be able to tell if an alien is happy or sad. So let's look at the data set. So these are the 4 sentences. Ak, 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 beep, beep, ak, beep, ak, and ak, beep, beep, beep. For each one of them, you're going to collect the number of times the word ak appears and the word beep appears. And now you're also going to collect the mood of the alien. So this is going to be a classification problem. Why? because given any sentence, the idea is to classify it as happy or sad. And because you're classifying it as happy or sad, this is called a sentiment analysis model. But everything works nicer with a plot. So let's make a plot of each of the sentences. In the horizontal axis, you have the number of times the word ack appears, and in the vertical axis, you have the number of times beep appears. And what's a model this time? Well, again, it's going to be a line. Let's say this line. Well, this line doesn't do very well. The idea of the model is to be able to classify or to split apart the happy points and the sad points. So for example, here's a better model. And as you train the model, let's say it gets to an ideal point here. And this ideal point here splits the plane into two regions. The sad region here shown in green and the happy region here shown in orange. And the idea is that if a new sentence comes in, depending on which area it is, the model will predict if the sentence is happy or sad. The model may make mistakes, but for the most part, it'll do well, at least based on how it did on this data set. So again, how does the model do this? Well, it turns out that there's a lot of mathematics driving the process of your model, the training process. Some of the math concepts involved are gradients, derivatives, optimization, loss and cost functions, gradient descent, and many, many more. So in this course, you're going to learn about model training and optimization and how it works at the core with mathematics. And in our scenario example, we use several models. We use linear regression, classification, examples to motivate the problem, but the techniques and concepts you're going to learn here can be applied to a wide range of other machine learning algorithms, such as, for example, neural networks. When I think of a derivative, the first thing that comes to my mind is velocity. So let's say, for example, that you're in a car and you go 100 kilometers in 1 hour. That means your average velocity was 100 kilometers per hour. However, maybe you started fast, then you went slow, then you stopped, then you went really fast, then maybe you went in reverse at some point. So this velocity is not constant. And so the question is, at a given instant, what is the velocity at that instant? And so that's called the instantaneous velocity. And that is precisely what a derivative is. A derivative is the instantaneous rate of change of a function. And in this case, the function is distance and its derivative is velocity. Let's add some numbers to this example to understand the concept of the derivative more clearly. Imagine here that you are in the car traveling on a straight road and you have a speedometer that tells you the velocity. Now remember from physics that speed equals distance traveled divided by the time elapsed. Unfortunately, the speedometer breaks. But now you have an app that tells you the distance you have traveled, and you also happen to have a calculator in your hand. So you drive for 1 minute and you're able to generate a table of values showing the distance you traveled every 5 seconds for 1 minute. Now here is the first quiz. The question is the car moving at constant speed? And the hint is, take a look at the distance values in the table. The car is not moving at constant speed. You can see that between 10 and 15 seconds, which is a 5-second interval, the car traveled 80 meters. But between 15 and 20 seconds, which is also a 5-second interval, the car traveled 63 meters. This tells us that from 10 to 15 seconds, the car was traveling at a faster average velocity than it was between 15 and 20 seconds. So we can also conclude that the speed of the car is not constant across the 1 minute interval. Great, so you've determined that the car is not moving at constant speed. Now here is the second quiz. Can you use this information to tell you your velocity at time 12.5 seconds? And the hint is that velocity equals distance traveled divided by time taken. So again, the quiz is, can you or can you not use this information to determine the exact velocity at 12.5 seconds? So the answer is no, you cannot find the velocity at time 12.5 seconds with the data given on this table. You can find the average velocity in the interval from 10 to 15, but you don't know what happened within that interval. At 12.5, maybe you were going faster, maybe you were going slower than the average velocity. However, there is one thing you can find. You can find the average velocity in the interval from 10 to 15 seconds. So that is the next quiz. What was the average velocity of the car in the interval from 10 to 15 seconds? So let's draw a graph for the points in the table to observe what's going on. And let's zoom specifically to the points 10, 122 and 15, 202 to find the slope at a point, because the slope is going to be the average velocity. So here is the graph and here is the interval. So the average velocity between the time interval 10 seconds to 15 seconds is also the slope of the line that joins the 2 points in the graph. Now velocity is calculated with a formula, distance over time. This is synonymous to the formula for calculating slope, which is rise over run. This is the rise and this is the run. In this case, the rise is the change in distance and the run is the change in time. This is because distance is on the vertical axis and time in the horizontal axis. The distance traveled at 15 seconds is 202 meters, and the distance traveled at 10 seconds is 122 meters. So the length of the time interval is 5 and the length of the distance interval is 80. Using the formula for slope or velocity, we get 80 divided by 5 equals 16 meters per second. The slope of the line that passes these 2 points is 16, which also translates to the velocity of the car between those 2 points is 16 meters per second. Now, while the average velocity between 10 to 15 seconds was a good estimate for the velocity at t equals 12.5 seconds, could we do better? Well, yes, we can if we had more data about the distances of time close to t equals 12.5 seconds. And so let's say that we take more refined measurements, one every second, and here you have a lot more data about the distances you traveled every second and a specific distance you covered from time t equals 10 all the way to t equals 20. And the data is shown in this table over here. So here is another quiz. Can you find a better estimate of the velocity of the car at time t equals 12.5 seconds using this data? So once again, we are not able to find the exact velocity of the car at 12.5 seconds. However, we have a way of making an even better guess than the previous one for what this velocity is by taking the average velocity between the interval of time between 12 seconds and 13 seconds. And how do we calculate this? Well, if the slope is the change in distance over the change in time, that's the velocity of the interval, then this is the distance at 13 minus the distance of 12 divided by the time at 13 minus the time at 12. Distance at 13 is 170, distance at 12 is 155, and the time difference between 13 and 12 is 1 second. So we get a slope of 15 meters per second. That's the velocity for that interval. And that is a much better estimate for the instant velocity at t equals 12.5. Now notice that we still don't have the estimate of the velocity at 12.5. What would you do to find this estimate? Well, you can just take finer and finer intervals. And the finer the intervals, the better the estimate is. And that leads to the derivative, which is coming next. In the previous video, you learned how to calculate the average velocity over an interval. But what is the instantaneous velocity at a point? Let's look at the point t equals 12.5 that you were looking at before. Calculating the instantaneous velocity here may be hard, but estimating it is possible. For example, let's take another point to the right of t equals 12.5 and calculate the average velocity over that interval. That is the slope of this line over here, which is exactly delta x, the change in distance, divided by delta t, the change in time. But that is not the instantaneous velocity at t equals 12.5. However, you can get closer to it by making this interval smaller. For example, take now this point over here closer to t equals 12.5, and the average velocity over that interval is the new delta x over the new delta t, which is the slope of this new line. And now let's put the point even closer to 12.5 and even closer. And now imagine putting it so close that you can't even tell the distance between the two. So you get the limit, which is dx over dt, and that is precisely the tangent line to the curve at t equals 12.5. So this measure of how fast the distance is changing with respect to time is called the instantaneous rate of change, and it is the slope of that tangent line. More generally, the instantaneous rate of change is a measure of how fast the relationship between two variables is changing at any point. In other words, imagine that you move a tiny distance dx in a tiny interval of time dt. This is the instantaneous rate of change, and it's also called the derivative. And the derivative of a function at a point is precisely the slope of the tangent at that particular point. So now that you know what a derivative is, let me show you a very interesting property of it. Let's go back to the table, but just as this little piece between 19 seconds and 20 seconds. Notice that the distance at 19 is 265 and the distance at 20 is 265. The distance is the same at both points. It hints that perhaps the car didn't move in that interval. Maybe it moved and then came back, but let's assume that it didn't move at all. So this is how the interval between 19 and 20 looks. The line between these points is a horizontal line, and a horizontal line has a slope of 0. Here's the calculation. The slope is the change in x over the change in t. And the change in x is the distance at 20 minus the distance at 19. And that is 265 minus 265. Now the change in t is 1 second. So the slope is 0 over 1 because there is no rise in distance. Distance doesn't change. Therefore, the slope is 0 meters per second. So now let's look at a trajectory of the car. We're going to plot it on the right. So first the car goes forward, then it stops, then it goes backwards, then it stops, goes forward again, then backwards again, and then forwards again. So here is a quiz question for you. Given this trajectory, where was the velocity of the car 0? So if you set that at any of the points where the tangent is horizontal, therefore the tangent has slope 0, you were correct. Those are the points where the car was stopped. And in total, there are 5 points. Now let me ask you another quiz question. At what time was the car farthest from its starting point? And the answer is over here, because this is when the distance was 50, and that's the highest distance that you can find in this graph. Now notice something interesting. The point where the distance was the farthest is coincidentally one of the points where the car was stopped. And this is no coincidence, because if the car is moving, then it could just go further. So the point where the car is the farthest is a point where the car is not moving. That means if you want to find the maximum or the minimum in a function, it occurs at one of the points where the derivative is 0. Or in other words, where the tangent line is horizontal. Like any language, mathematics has its way of expressing concepts. In this video, I'm going to show you 2 ways to express the derivative. The first one is Leibniz notation, and the second one is Lagrange notation. Let me show you how they work. So first recall that the slope was calculated as the change in distance over the change in time. That's delta x over delta t. And that the slope of a tangent at a point was called dx over dt. Now what was this dx and this dt? Well, in order to calculate the slope, you first started with a big interval, calculated delta x over delta t. That's the slope of that secant, and then made the interval smaller and smaller, always calculating delta x over delta t, until the interval was so tiny that you get the tangent line. And this slope was called dx over dt. Now dx over dt represent infinitesimal changes in the x direction and in the t direction. So that's one way of writing the derivative, as dx over dt. Now, in general, we're going to have x as the horizontal axis and y as the vertical axis. So the derivative is going to be called dy over dx instead. So here's some notation. Let's say that your function is called f of x, and that's y. So y is f of x. Now the derivative of x can be expressed in two ways. One is as f prime of x. So recall the function is f, and at the point x, the slope of the line is f prime of x. That is Lagrange's notation. And the other one is the one you just saw, which is dy over dx. That can also be expressed as d over dx of f of x. In this case, d over dx can be thought of as an operator, something that when you apply to f of x, you get something else. And this is Leibniz notation. So sometimes in this course, we're going to use Lagrange notation, f prime of x, and other times we're going to use dy over dx, which is Leibniz notation. And we're normally just going to pick the one that's more convenient. Our goal is to be able to calculate the derivatives of most of the functions that we know. So let's start with the simple ones. What are the simple ones? Constant functions, linear functions, quadratics, polynomial functions, exponential and logarithmic functions, and the trigonometric functions. You're going to be glad to know that these have very nice and simple derivatives. So let's start with lines. And the simplest line is actually a constant, so a horizontal line. This function is such that the height at every point, for example x0 and x1, is always the same, some constant c. The c could be -1, 7, 3.5, any number as long as it's always the same. So now let's look, for example, at the derivative at x0. So this tangent line has the same slope as the entire line. What is this slope? Well, the slope is delta y over delta x. Now the change in y is always 0 because y is always c. So it's always c minus c. And therefore the numerator here is 0 and the denominator is not 0 if we take x0 different than x1. So therefore this slope is always 0, and we conclude that a horizontal line or a constant always has a derivative of 0. Now let's consider some generic line that is not horizontal, so it can have the equation f of x equals ax plus b, where a is the slope and b is the y-intercept. What is the derivative for this function? Well, this derivative is very simple. Let's take a point, for example this one, and we're going to calculate it by taking any other point and looking at delta x, looking at delta y, and calculating the slope delta y over delta x. Now this is rise over run, so it's going to be a, which is the slope. Now notice that as the second point gets closer to the first one, well, the tangent stays of the same slope for the same reason as what happened with the constant line. When you have a line, the tangent at every point has the same slope as the entire line, and this line has a slope of a. Therefore, the equation f of x equals ax plus b of a line has a derivative f prime of x of a. And if you want to see the math happening, well, let's look at the points. This point has equation x ax plus b. Those are the coordinates. And this point has coordinates x plus delta x, ax plus delta x, b plus b. Therefore, when we take the slope, it's delta y over delta x, and that's the difference between this number and this number, the delta y. So that's ax plus delta x plus b minus ax plus b. And the denominator is delta x. So a lot of things cancel out here. This ax cancels out with this ax. This b cancels out with this b. And then we have a times delta x over delta x. The two delta x's cancel out. And the slope is a. Therefore, the derivative of the line with equation ax plus b is the slope a. So now that you know lines, let's take a look at a slightly more complicated function, quadratics. The simplest quadratic is this parabola with equation y equals x squared. Let's look at the derivatives. Notice that to the left of the y-axis, these are negative, and to the right of the y-axis, these are positive. The formula for the derivative is delta f over delta x as delta x goes to 0. Now delta f is the change in y, or the change in f, which is x plus delta x squared minus x squared. So before we do this formally, let's take a look at an example. What happens when x equals 1? Then y is x squared, which is also 1. So let's take a look at some secants, calculate their slope, and with that we calculate the slope at the tangent line. So let's start with a delta x of 1. That means an interval of length 1 horizontally. So what is delta f when delta x is 1? Well, it's the difference between 4 and 1. 4 is 1 plus 1 squared, and 1 is 1 squared. So this is 3. And what's the slope? Well, it's going to be 3 over 1, because delta f is 3, delta x is 1, and so 3 over 1 is 3. So this slope is 3. Now let's make the interval smaller and see what happens. If we make this interval of length 1 over 2 horizontally, then delta x is 1 over 2. What is delta y or delta f? Well, it's going to be 1 plus 0.5 squared minus 1 squared, which is 2.25 minus 1, which is 1.25. And the slope is 1.25 over 1/2. And that is a value of 2.5. Now let's make an interval even smaller. Let's make it of length 1/4 horizontally. So what is delta f now? Well, delta f is 1 plus 0.25 squared minus 1 squared, which is 0.56. And the slope is 0.56 divided by 1/4, and that is 2.25. Now let's continue making this interval smaller to see where the slope goes. It went from 3 to 2.25 to 2.25. Where do you think it's going to go? So let's look at an interval of length 1 over 8. The slope is going to be 2.125. At an interval of 1 over 16, the slope is 2.065. And let's go extreme. Let's do an interval of 1 over 1,000. The slope is going to be 2.001. So it looks like the slope is going towards 2. And that's actually the answer. The slope at the tangent at 1 is 2. And notice that 2 is 2 times 1, and that's actually the formula, because the derivative of x squared is 2x. So let's actually calculate it formally. What's delta f over delta x? Well, delta f, just like above, it's x plus delta x squared minus x squared divided by delta x. So let's expand that and let's cancel some things out. The x squared goes with the minus x squared, the delta x goes with the delta x, and you get 2x plus delta x. Now, what's the value of 2x plus delta x as delta x goes to 0? Well, the 2x stays put, and this delta x is 0. So therefore, the derivative df over dx is going to be 2x. So when f of x equals x squared, then the derivative is f prime of x equals 2x. So now that you know lines and quadratics, let's go to cubics. The simplest cubic is the function y equals x cubed, seen over here. And here are some of the slopes of the tangents. Again, the formula is very similar from before. It's x plus delta x cubed minus x cubed divided by delta x, and then as delta x goes to 0, then this value becomes the slope of the tangent line, or the derivative. So let's do a small example where x is equal to 0.5. When x is 0.5, then y is 1/8, because 1/2 cubed is 1/8. So let's take some intervals and calculate the slope of the secant lines. If delta x is 1, then we have the point 3/2, which is 1/2 plus 1, and 27 over 8. Why 27 over 8? Because 1/2 plus 1 cubed is 27 over 8. So we subtract 1/2 cubed, and we get 3.25. And the slope of this secant line is going to be 3.25 divided by 1. So that's 3.25. Now let's decrease the interval to length 1/2 and do the same calculation. So x plus delta x cubed is 1/2 plus 1/2 cubed, which is 1, minus 1/2 cubed, which is 1/8. So we have 7/8, which is 0.86. And the slope is 0.86 divided by 1/2, which is precisely 1.75. Now let's go even smaller. Let's go for 1/4. And I'll do the calculations quickly, but I invite you to do them on pen and paper if you'd like. Delta f here is 0.3 and the slope is 1.188. For 1/8, then delta f is 0.12 and the slope is 0.12 divided by 1/8, which is 0.95. For 1/16, we have a slope of 0.85. For 1/1000, we have a slope of 0.752. And as you see, these values tend to converge to 0.75. And that's actually the value. F prime of 0.5 is 0.75. That's actually 3 times 0.5 squared, because the derivative of x cubed is actually 3x squared. But let's actually calculate it formally to see that this is the case. So delta f over delta x is going to be x plus delta x cubed minus x cubed, that's the change in y direction, in the vertical direction, divided by delta x, which is a change in the horizontal direction. Now expanding a cube is a little harder than expanding a square, but this is what you get. And if you cancel out the x cubed, if you divide top and bottom by delta x, then you get 3x delta x plus 3x squared plus delta x squared. Now, as delta x goes to 0, what happens with 3x delta x plus 3x squared plus delta x squared? Well, anything that has a delta x becomes 0. So the only thing that stays put is the 3x squared. And that's the derivative. So if f of x equals x cubed, then f prime of x equals 3x squared. And that's the derivative of this cubic. So now that you know lines and some polynomials, let's look at a complicated one, 1 over x. This is a hyperbola that looks like this. And let's take a look at some of the tangent lines. The function looks more complicated, but actually the calculation is quite simple. For the calculation, one would do x plus delta x inverse minus x inverse divided by delta x. So let's look at the point x equals 1 and y equals 1. And let's take some intervals just like before. So if the interval is of length 1 horizontally, delta x equals 1, then what is delta f? Well, delta f is going to be the change in the vertical direction. So x plus delta x inverse minus x inverse for x equals 1. That means it's 1/2 minus 1. And that's minus 0.5. And so the slope is minus 0.5 divided by 1. Which means that the slope here is minus 0.5. Now let's decrease the length of the interval. Let's make it so that delta x is 1/2. If delta x is 1/2, then what's delta f? Well, it's 1 plus 1/2 inverse minus 1 inverse, which is 2/3 minus 1, which is minus 1/3. And delta x is simply going to be 1/2. So the slope is 0.33 divided by 0.5, which is minus 0.67 or minus 2/3. Now let's do some more, and again I'll go a little fast with the calculations. For 1/4 the slope is minus 0.8, for 1/8 is minus 0.89, for 1/16 is minus 0.94, and for 1/1000 it's minus 0.999. So as you can see, this converges to minus 1, and so the derivative here is negative 1. This is negative 1 times 1 squared, which is actually the value, because when f of x equals x inverse, then the derivative is minus 1x to the minus 2. Let's actually do the calculation to confirm this. So delta f over delta x is going to be x plus delta x inverse minus x inverse divided by delta x. So let's actually write this as 1 over x plus delta x minus 1 over x over delta x. And let's expand the 1 on the top as x minus delta x plus x divided by x plus delta x times x. And some things cancel out. This plus x and this minus x cancel out. We can multiply and divide by delta x. And we get minus 1 over x squared plus delta x. And now, as delta x goes to 0, well, the 1 on top stays put, the x squared stays put, but this goes to 0. So therefore, we have 1 minus 1 over x squared. So if f of x equals x inverse, then f prime of x equals minus 1 times x to the minus 2. So let's take a look at what we've learned so far. The derivative of x squared, x cubed, and x inverse we've already calculated. The first one is 2x to the 1, the second one is 3x squared, and the third one is minus 1x to the minus 2. Now, can you spot a pattern? These three actually follow a really nice pattern. And that works for any power function. So, take a look at the exponent. The exponent goes here in the derivative as a multiplication factor. And then you subtract 1 from the exponent and you get the new exponent. So x squared becomes 2x to the minus 1. X cubed becomes 3x squared. And x inverse, so x to the minus 1, becomes minus 1 x to the minus 2. So what do you think happens with x to the n? Well, with x to the n, the exponent of n comes down and it becomes n. X to the new exponent is n minus 1. So nx to the n minus 1. So if you have any power function, for example, x to the 100, the derivative is 100x to the 99. And if it's x to the minus 100, the derivative is minus 100x to the minus 101. So now that you learned the derivatives of several functions, here's an important concept that's going to help you find the derivative of more functions. It's the concept of the inverse function. Now, what is an inverse function? Well, if your function does a certain thing, then the inverse function is the one that undoes that thing. So for example, if the function f sends the number 3 to the number 5, then the inverse function sends the number 5 back to the number 3. And now, you're going to learn that if you know the derivative of function f, then the derivative of the inverse function is actually very easy to calculate because they are very well connected. So the mental image I have of an inverse function is the following. Let's say that you have a person and the function f does something to the person. It puts a hat on them. What would the function g have to do if it's the inverse? Well, it would just remove the hat so that you get the original person back. In other words, the inverse does the opposite of what f does. So it undoes what f does. In a more mathematical example, let's say you have the variable x and f puts on a hat on it, so it squares it, let's say. So what would g have to do? Well, undo the square, so remove the hat. G is the function that takes as input x squared and returns x. Before we get to see what f and g are, let's take a look at some notation. So if g of x and f of x are inverses, we write this as g of x equals f inverse of x with an exponent of minus 1. But this is not 1 over f of x. This is purely notation. And if you take x and apply f and then apply g, you get back the x you started with. So basically g undoes what f does. So what are f and g in the example on the left? Well, f is easy. It's simply x squared. And g is the function that undoes a square. So it's basically square root of x. And the reason is that if you take x and square it and then take the square root, you get back x. And this is only for x positive numbers. And also we're only taking the positive square root, not the negative. But in short, if f does something, g has to undo it to get your first input back. Now the derivatives of inverses are really nice. Let's take a look at the plot of x squared and now the plot of g of y equals square root of y. Notice that in this plot, the units are different in the left and the right. And also in the plot in the left, the horizontal axis is x, and in the plot on the right, the horizontal axis is y. But in short, if a point with coordinates AB appears on the left, then the point with coordinates BA appears on the right. So for example, on the left, we have the point a half, a quarter. On the right, we have the point a quarter, a half. And this is because a quarter is the square of a half, and a half is the square root of a quarter. So the point, basically f1 half is equal to 1 quarter, and g of 1 quarter is equal to 1 half. The point 1, 1 also appears on both, because f of 1 is 1, as 1 squared is 1, and g of 1 is 1, because the square root of 1 is 1. The point 3 halves, 9 fourths also appears on the left, and the point 9 fourths, 3 halves appears on the right, and similarly, the point square root of 3, 3 appears on the left, and the point 3 square root of 3 appears on the right. Now, I want you to take a careful look at the tangents over these points in the left plot and in the right plot. And let's question yourselves. Do you think there's a connection between the slopes of the tangents on the left and the slopes on the tangents of the right? Well, consider that the plot on the right is the reflection of the plot on the left over the diagonal y equals x. So there's got to be a really nice connection between these slopes. Let's take, for example, a secant. Before we draw tangents, let's draw a secant. So let's take the point 1, 1, which is on both plots. And let's take the point 1.5, 2.25 on the left, because 2.25 is the square of 1.5. And the point 2.25, 1.5 on the right. So let's calculate the slope of this secant line. On the left, it's delta f divided by delta x. So the change in the vertical coordinate divided by the change in the horizontal coordinate. And on the right, this is going to be delta g over delta y, where delta g is the change in the vertical coordinate and delta y is the change in the horizontal coordinate. However, these plots are a reflection of the other. So therefore, any horizontal distance on the left is equal to the vertical distance on the right and vice versa. In other words, this delta g is the same as this delta x, and this delta y is the same as this delta f. So therefore, the slope delta g over delta y is the same as delta x over delta f. Now notice that as delta goes to 0, f prime of x is delta f over delta x. And equally, as delta y goes to 0, then g prime of y is delta g over delta y. So putting this together, we get that g prime of y is 1 over f prime of x. And this looks complicated, but it only says that if f and g are inverse functions, then the derivative of g is 1 over the derivative of f. So let's look at a simple example. And this time we have two plots of x squared and square root of y, where the actual units are going to be the same on the left and on the right. So each square is 1 by 1. So let's look at the tangents. So at the point 1, 1, we have that f of 1 is 1 and g of 1 is 1. So the point 1, 1 appears on both plots. Now take a look at the tangent on the left. Since f prime of x is 2x, because it's the derivative of x squared, then f prime of 1 is 2, which means that this orange line has a slope of 2. Now let's take a look at the slope on the right, the tangent. G prime of y is what we want to find. We want to find the slope of that tangent. Well, since g prime of 1 is 1 over f prime of 1, then this is 1 over 2, which is a half. Therefore, a half is the slope of the tangent on the right. So it makes sense, right? If the slope of the tangent on the left, the orange one, is 2, then the slope of the tangent on the right is 1/2, the reciprocal of 2. Now let's do another example, the point 2, 4. So on the left, we have the point 2, 4, and on the right, we have the point 4, 2, because f of 2 is 4 and g of 4 is 2. Now the slope on the left, well, since the derivative f prime of x is 2x, then f prime of 2 is 4, which is 2 times 2. So what do you think this slope is going to be? Well, it's probably going to be 1/4, right? Because it's 1 divided by the slope on the left. And indeed it is, because g prime of 4 is 1 over f prime of 2, and that's 1/4. So in other words, if f and g are inverse functions, then the derivative of g is 1 over the derivative of f. So let's take a look at another family of functions, the trigonometric ones. So let's start with the sine function. And let's consider a few particular points. Minus pi over 2, pi over 2, 0, and minus pi. Let's look at the slopes at these points. So the slope at pi over 2 is 0. The slope at minus pi over 2 is 0. The slope at 0 is actually 1. And the slope at minus pi, it's going to be minus 1. That's the one on the left. Now let's compare it with the function cosine. And now we're not going to look at the slopes, we're actually going to look at the values. So at pi over 2, the value of cos is 0. At minus pi over 2, it's 0. At 0, it's 1. And at minus pi, it's minus 1. Do you think this is a coincidence? Actually, it's not. It's always the case that if f of x is sine of x, then the derivative f prime of x is the cosine of x. And why would this happen? We'll take a look at it in a minute, but it's a really, really nice property. Now, the same thing happens in the opposite way, except with a minus sign. So if this is cosine, let's take a look at some slopes. At 0, minus pi, pi over 2, and minus pi over 2. At 0, the slope is 0. At minus pi, the slope is 0 again. At pi over 2, it's minus 1. And at minus pi over 2, it is 1. And now let's look at sine of x, but the values now. So at 0, you get 0. At minus pi, you get 0. At pi over 2, you get a 1. And at minus pi over 2, you get a minus 1. So it's almost the same. We just have to flip it with a sign. So if f of x is cos x, the derivative is negative sine of x. And again, we'll see that why in a minute. But this is something to remember. The derivative of sine is cosine, and the derivative of cosine is negative sine. There's a nice geometric reason why this works, and take a look. Let's take a circle of radius 1 and let's draw any radial line, and x is the angle between the horizontal axis and the line. The projection over the x-axis is cosine of x, and the projection over the y-axis is sine of x. Now let's move the angle x slightly by a quantity of delta x. Now the projection on the horizontal axis is going to be cosine of x plus delta x, and the projection over the vertical axis is going to be sine of x plus delta x. And now let's focus on this orange triangle over here, and let's actually blow it up a little bit. This triangle has one base equal to negative delta cosine of x, and the other side is delta sine of x. Now we can call the top angle phi and the hypotenuse h. So if you recall from trigonometry, there's a rule that states that given a right triangle, the cosine of one of the angles is equal to the adjacent side divided by the hypotenuse. The adjacent side here is delta sine x, while the hypotenuse is h. Now given that delta sine x equals h cos phi. Similarly, there's a rule that states that the sine is equal to the opposite divided by the hypotenuse. In this triangle, the opposite side is negative delta cos x, while the hypotenuse is again h. Therefore, negative delta cos h is h sine of theta. Now what happens as delta gets smaller and smaller? Well, the hypotenuse of this triangle almost coincides with the arch of the circle and approaches delta of x. The angle phi approaches x, and with these new values we get that delta sine x equals delta x cos x, and negative cos x equals delta x sine x. Also, delta sine x divided by delta x goes to the derivative of sine x, and delta cos x divided by delta x is the derivative of cosine of x. And this actually confirms the intuition you built before. So sine prime of x is cos x, and cos prime of x is negative sine x. So let's set our eyes in a very important function, the exponential function. And for this, we need to define Euler's number. Euler's number is quite a special number in mathematics. It appears in many, many branches. And it can be defined in many ways. One of them is by the numerical value, 2.71828182, etc. The decimal never terminates because the number is irrational, which means it cannot be expressed as a ratio between two integers. Another way to define it is using the expression 1 plus 1 over n to the n. Let's look at this expression for several values of n. For 1, it's 1 plus 1 over 1 to the 1, which is 2. For 10, it's 1 plus a tenth to the 10, which is 2.594. For 100, it's 2.705. For 1,000, it's 2.717. And as you notice, the more we increase n, the more this converges to a certain number. The actual number that this gets closer and closer is e, 2.71828182, etc. So that's how we're going to define the number e. And e has a very particular property. If you consider the function f of x equals e to the x, that function is its own derivative. So the derivative of f of x is also f of x. And that particular property makes sure that E appears in many places in science, statistics, probability, etc. Now, the way I like to define E is using interest rates. So let's look at the following problem. Let's say that you're trying to find the best bank where to put your money. So bank 1 says the following. Bank 1 says, I'm not going to give you any money for a year, but after a year, I will give you as interest 100% of your money. That means all your money once a year. Means if you put in $5 today, in a year, they give you another $5. So that's pretty good, but you continue looking. Let's go to bank number 2. Bank number 2 says, well, I'm going to give you 50% of your money every 6 months. So if you put in $10 today, in 6 months, you're going to have $15. Because bank 2 gives you half of your money twice a year. And bank 3 is slightly different. This one says, I'm going to give you 1/3 of your money 3 times a year. So 33% every 4 months. So in summary, bank 1 gives you all your money once a year. Bank 2 gives you half of your money twice a year. And bank 3 gives you 1/3 of your money 3 times a year. The question is, which bank is better? So let's take 5 seconds for you to figure out. And if you need more time, feel free to pause the video and think about it. This is a very important problem. So the answer is that bank 3 is the best bank of the 3. Why? Well, let's say you have $1. So bank 1, after a year, gives you another one. So you end up with $2. Now the question is, what are you going to end up with in bank 2? And what are you going to end up with in bank 3? In other words, what's the percentage that you end up getting in a year in bank 2 and bank 3? So let's take a look. Bank 1, you have $1 now. And in a year, you're going to have your dollar plus the extra dollar that bank 1 gives you of interest. That's $2. We can express the 2 as 1 plus 1 to the 1. That's going to be important later. In bank 2, now you have $1. And in 6 months, you have $1 plus a half. And in 1 year, you're going to have $8 plus a half of that. So in 6 months, you end up with 1 plus a half, which is 1.5. And in 1 year, you end up with 2.25, which is 1 plus a half squared. This is because you're adding half of your money, which means you're multiplying it by 1 plus 1/2 every time. And 2.25 is bigger than 2 because your dollar got doubled. But this amount of money that you actually earned more money later. So this is called accrued interest, the money that gains interest, and then that interest gains interest. And that's why you did better with bank 2 than with bank 1. Now let's take a look at bank 3. So in bank 3, you start with $1 right now. In 4 months, you have $1 plus 1/3, which is 1.33. In 8 months, you have your 1 1/3 plus 1/3 of that, and that's 1.77. And in 1 year, you have 1.77 plus 1/3 of that, which is 2.37. And again, you did well because this interest over here accrued interest and accrued more interest, and this interest over here accrued more interest. So your money is making more money. At the beginning of the year, you had $1, then you had 1 plus 1/3, then you had 1 plus 1/3 squared, and then you had 1 plus 1/3 cubed. And that becomes 237. So in short, in bank 1, after 1 year, you have $2. In bank 2, after 1 year, you have 2.25. And in bank 3, after 1 year, you have 2.37. That's why the money is better in bank 3. And this money actually multiplies a lot. Take a look at what happens in bank 1 after 4 years. You're going to end up with $16. In bank 2, after 4 years, you're going to end up with more money. You're going to end up with $25.63. And in bank 3, you're going to end up with quite a lot of money. You're going to end up with $31.57. So definitely bank 3 is much better than bank 1 and bank 2. And again, let's recall that after 1 year, in bank 1, you get 1 plus 1 to the 1. Bank 2, you get 1 plus 1/2 to the 2. And in bank 3, you get 1 plus 1/3 to the 3. And this is super important. Now, could you imagine a better bank than these 3? Well, of course, the more subdivisions you have, the better. Let's look at bank 12. Bank 12 gives you 1/12 of your money every month. So you start with $1 now. In a month, you have 1 plus 1/12. In 2 months, 1 plus 1/12 squared. and so on until in 12 months you have 1 plus 1, 12 to the 12. And that's $2.61. So you did much better. So in general, bank N would have N subdivisions. It subdivides the year into N intervals, and every time it gives you 1/n of your money. So you start with 1 on the first day, after the first interval, 1 plus 1 over n. After the second interval, 1 plus 1 over n squared. And if this is not super clear, let me elaborate. 1 plus 1 over n is the money you have, and you add an nth of that. So you have 1 plus 1 over n plus 1 over n, 1 plus 1 over n, and that is the money you have plus the interest you accrue. And that factors as 1 plus 1 over n squared. After 3 intervals, you have 1 plus 1 over n cubed. After k intervals, you have 1 plus 1 over n to the k, and eventually, after the end of the year, you have 1 plus 1 over n to the n. And n can be really large, so you could potentially accrue money every second or every millisecond. And in summary, bank N does the following. It gives you 1 plus 1 over n to the n at the end of the year because it returns 1/n of your money n times a year. So now imagine that you go around looking for banks. There's bank 1, there's bank 2, there's bank 3. Bank 4 gives you 1/4 of your money 4 times a year. Bank 5 gives you 1/5 of your money 5 times a year, and so on until the end of the universe. So here's bank 12 that gives you 1/12 of your money every month. Here's bank 365 that gives you 1/365 of your money every day. And what's at the very, very, very end of the universe? What is this bank? Well, this bank, let's call it bank infinity. And what bank infinity does is it pretty much gives you instant interest. 1/infinity of your money infinity times a year. So let's see how much money bank infinity would give you at the end of the year. So bank 1 ends up with 1 plus 1 to the 1. Bank 2 with 1 plus 1/2 to the 2. 1/3 is, bank 3 is 1 plus 1/3 to the 3. Bank 12 is 1 plus 12 to the 12. Bank 365 is 1 plus 1 over 365 to the 365, which already is 2.7145. And bank infinity gives you, well, this is not a good mathematical expression, 1 plus 1 over infinity to the infinity, but it's basically the number that all these numbers converge to: 2.25, 2.37, 2.613, 2.7145, etc., etc., etc. Gets closer and closer and closer to a particular number, and that number is 2.71828182, or the number E. So E is the amount of money that you get at the end of the year in bank infinity. If bank infinity gives you an infinitesimal of your money every single instant. And that is one way to look at the number E. In the previous video, you learned something very interesting, the Euler number E. And one very important property of the number E is that if you take the function y equals e to the x, this is called the exponential function, and this function is its own derivative. In other words, if you take a point x, then the point in the graph is the point x comma e to the x, which means that that height is e to the x. Well, if you take the tangent at that point, the slope of that tangent is actually e to the x. So e to the x is equal to its own slope. Now let's verify this numerically by taking some measurements. So here is y equals e to the x again, and we're going to calculate the slope of some secant lines in the same way that you've done it before. Let's take, for example, the number x equals 2. So the point in the graph is 2, 7.39, because 7.39 is e squared. Now let's take some intervals and calculate the slopes of these secants. So for example, if we move to the right 1 unit, then delta x is 1, and delta f is just going to be e to the 3 minus e to the 2, and that's exactly 12.7. So the slope is 12.7 divided by 1, which is 12.7. Now let's reduce the interval to length 1/2. The delta f is now 4.79 because it's e to the 2 plus 0.5 minus e to the 2. And delta x is 1/2. So the slope is 4.79 divided by 1/2, which is 9.59. If we do it for a quarter, then delta f is 2.1 and the slope is 8.39. If we do it for an eighth, then the slope is going to be 7.87. For 1/16, it's 7.62. For 1/1000, it's going to be 7.39. And as you can see, these numbers approach a particular number. The number that it approaches is actually e squared, 7.39. And so here we verified numerically that the slope of the tangent line at the point 2e squared is precisely e squared. And this is what happens at every point. The tangent at the point x comma e to the x has slope e to the x. And that's a fascinating property of the function e to the x. In the previous video, you learned the exponential function e to the x, where e is the Euler number. And you learned the property that it has, which is that the derivative of e to the x is e to the x. In this video, you're going to use that and the inverse function rule in order to calculate the derivative of the logarithmic function. And you're going to see that it's actually very simple. But before we get to derivatives, let's look at what's a logarithm. Imagine that you want to find a number such that e to the that number equals 3. That number is precisely the logarithm of 3. And that actually works for any number x. If I want to find the number such that e raised to the that number is x, that number is logarithm of x. We also call it the natural logarithm. You may see in other places logarithms in other bases, such as 2 or 10. But in this course, it's always going to be base e or the natural logarithm. Now, the fact that e to the logarithm of x is x means that the function f of x equals e to the x has an inverse, which is logarithm of y. F inverse of y is the logarithm of y. Because e to the logarithm of x is x, and logarithm of e to the y is y. Now let's plot them. On the left, we have the plot of e to the x, and on the right, we have the plot of logarithm of y. So as usual, the left plot has as a horizontal axis x, and the right plot has a horizontal axis y. And let's look at some points in the plot on the left and their corresponding points in the plot in the right. And these correspond to each other because recall that the fact that these functions are inverses means that if we reflect one about the line with equation y equals x, we get the other one because logarithm of x is the inverse of e to the x. And now let's take a look at the derivatives. So we're going to use the results for inverses in order to calculate the derivative of logarithm of x. And you're going to see that's actually very simple. So let's take one point. For example, on the left we have 2, 7.89. Recall that 7.89 is e squared. That means that on the plot on the right, we're going to have the point 7.89, 2, which is e squared, 2. The derivative of this tangent, the slope of this tangent is the one we're going to find, and we're going to use this one over here. So recall that the slope on the right is 1 over the slope on the left. That's what we're going to use. The slope on the left is f prime of x equals e to the x. That's the derivative, because recall that the derivative of e to the x is e to the x. So therefore, because x is 2, the slope here is f prime of 2, which is e to the 2, or e squared. That's precisely 7.89. So the height at 2 is 7.89, and the slope at the tangent at 2 is also 7.89. So now what's the slope on the graph in the right? Well, because it's the reciprocal of e squared, then it's 1 over e squared. So this tangent of the line on the right, the slope is 1 over e squared. And notice that e squared is y. So therefore, g prime of y is simply 1 over y. Therefore, the derivative of logarithm is 1 over y. Let's do this mathematically. So using the result for inverses, d over dy of f inverse of y is 1 over f prime of x. Now x is f inverse of y, so let's actually write it like this. So if you take the logarithm function and you take the derivative with respect to y, then you get 1 over f prime of f inverse of y. Now f prime is e to the x, and f inverse of y is logarithm of y. So you get 1 over y. In other words, the derivative of logarithm of y is 1 over y. In the previous videos, you learned about some common functions and their derivatives. However, it's not always the case that you can find the derivative of a function at every point. For these functions where you cannot find the derivative at every point are called non-differentiable functions. So in this video, I'm going to show you several non-differentiable functions and how they can be identified visually. So far, you've learned that to find the derivative of a function at a point, you draw a tangent line to the point on that line and find the slope to the tangent. So for example, at this point over here, you would say that a function is differentiable at a point if the derivative exists for that point. That means if you can draw a unique tangent to the curve at that point. So for this curve, for any point you pick, you can draw a tangent and it's well defined. And we also say that for a function to be differentiable at an entire interval, then the derivative has to exist for every single point in that interval. However, some functions don't satisfy this property. We call them non-differentiable functions. Let's take a look at one. For example, the function absolute value of x. What's the absolute value of x? Well, it's kind of the positive part of x. So absolute value of 7 is 7, but the absolute value of -7 is 7. It can be defined like this. It's x for x bigger than or equal to 0 and -x for x less than 0. So this function is differentiable almost everywhere except for this point in the origin, because if you try to draw a tangent, well, it's not very well defined. All of this would work and it's not a well-defined tangent. So we say that at x equals 0, the derivative does not exist. And this always happens when a function has a corner or a cusp. If that's the case, the function is not differentiable at that point. That means if you're drawing it with a pencil and at some point you have to stop and draw a corner, then you have a function that's not differentiable at that point. So here is a quiz. If I give you this function, can you tell me at which point is this function not differentiable? So at which point does the derivative not exist? And so if you said that the derivative does not exist at x equals 1, then you were correct, because here we can draw multiple lines and neither one of them is well defined as the derivative at that point. So we say that the entire function is not differentiable because a derivative does not exist for every single point in the domain. Now consider this function. The function is defined as 2 for anything smaller than -1, and for anything bigger than -1 is this diagonal here defined by y equals x plus 1. So at which point in this function does the derivative not exist? This is a step function or a piecewise function. It has a jump discontinuity at x equals -1. Over here, as I mentioned, is defined as y equals 2, and over here is y equals x plus 1. So we say that at the point -1, there is a jump discontinuity. If you try to draw this function with a pencil, what's going to happen is that you have to at some point lift the pencil and start drawing it somewhere else. So the function is not continuous. And a function that is not continuous, that has a jump like this, is not differentiable because the derivative cannot be defined at this point. What line could you draw here that was the tangent? That is not well defined. So in general, any function that has a discontinuity is not differentiable at that point. And now let's do one more. This one is a little more subtle. Let's say we have the function f of x equals x to the 1/3. It looks to be differentiable at every point, but what happens at the origin? The tangent is parallel to the vertical axis. It's a vertical tangent, and that is not good. At x equals 0, this has a tangent line that runs straight up to the y-axis, and that means it's not differentiable. Why? Well, because a vertical line doesn't have a well-defined slope. It would be some number over 0, because the rise is any number, but the run is 0. So it's not well defined. One could say it's infinity, or one could say it's undefined, but the fact is that a function with a vertical tangent is not differentiable. So as a small recap, there are 3 types of not differentiable functions. Anything with a cusp or a corner, anything with a jump discontinuity, and anything with a vertical tangent. So corners, cusps are bad, jump discontinuities are bad, and vertical tangents are bad because these are all non-differentiable functions. So far, you've learned derivatives of some simple functions. In order to find the derivatives of more complicated functions, what you have to use is certain rules in order to piggyback from these simple ones into more complicated calculations. The rules you're going to learn next are multiplication by scalars, sum rule, product rule, and the chain rule for compositions of functions. So the first rule is multiplication by scalars. Let's say you have a function f and it's 4 times a function g. If you want to take the derivative of f, that means it's just going to be 4 times the derivative of g. And that works for every value of 4. So if it's actually a constant c, can be any constant, then if f is equal to c times g, then f prime is equal to c times g prime. Let's take a look at why this happens. So consider the function y equals x squared drawn over here. And let's take twice that function, so 2x squared. Therefore, the function gets multiplied by 2. So let's look at some points. On the left, you have the point 1, 1 and the point 2, 4, because 2 squared is 4. And so the slope of this secant line, well, it's rise over run, where the run is 1, which is 2 minus 1, and the rise is 3, because that's 4 minus 1. So this slope is 3 over 1, which is 3. Now let's look at the corresponding points in the function in the right, which, as we said, it's double the function in the left. The point corresponding to 1, 1 is 1, 2, and the point corresponding to 2, 4 is 2, 8. And let's calculate the slope. Well, the run is the same as the run in the previous one, which is 2 minus 1 equals 1. But the rise is double the previous one, because in the plot on the right, everything gets doubled in the vertical direction. So the 4 minus 1 equals 3 on the left, which is the rise, becomes an 8 minus 2 equals 6 on the right. And so the slope multiplies by 2, because the numerator multiplies by 2 and the denominator stays the same. Therefore, if the function multiplies by 2, all these slopes get multiplied by 2. Now, if you take the limit, if you let the point on the right move towards the point in the left, you still have that all the slopes multiply by 2. Therefore, the derivative, or the slope of the tangent, which over here is 2 as we saw before, now becomes 4. In other words, if we take a function and multiply it by 2, the derivative gets multiplied by 2. And this happens for every value. So for example, if we have a function like this, and we multiply it by c, which means the height of the right is c times the height on the left at every point, then the derivative gets multiplied by c. So if we have a point over here, x comma y, with slope f prime of x for the tangent line, on the right, the point corresponding to that is going to be x cy, and the slope is going to be c times f prime of x. Because if you think about it, the plot on the right is obtained from the plot on the left by basically putting your hands on top and bottom and stretching it by a factor of c. So that is the multiplication by scalar rule. So now that you know the scalar multiplication rule, the sum rule is just as simple. Imagine that you have a function f and it's expressed as the sum of two functions g and h. So what is the derivative of f? Well, it's simply the derivative of g plus the derivative of h. I like to imagine the sum rule in the following way. Imagine that there's a boat and there's a kid inside the boat. And the boat moves and the child also runs inside the boat. So the boat moves a distance, let's say, of 10, and the child moves a distance of 2. And we're going to keep track with variables xb for the distance that the boat moves and xc for the distance that the child moves. So if they're moving in the same direction, what is the distance that the child moves with respect to the earth? Well, that distance is 12 because it's 10 plus 2. It's the distance that the boat moves plus the distance that the child moves inside the boat. Now that's with distances, but what happens with velocities? So let's do a quiz. Let's say that the speed of the boat is 0.6 meters per second, and the speed of the child inside the boat is 0.05 meters per second, and they're both traveling in the same direction. So here is a question. What is the speed of the child with respect to the earth? So if you answered 0.65 meters per second, then you are correct, because velocities can be added if they are taken in the same direction. And that's pretty much the sum rule. It says if distances can be added, then velocities can also be added. Means that if functions can be added, then their derivatives can be added. So let's look at it with a plot. Here is a plot of time in the horizontal axis and distance in the vertical axis. And this is how the child moves inside the boat. This is how the boat moves. And this is the sum of the two, which is how the child moves with respect to the earth. So let's look at some slopes. Here is some point in time, and we're going to take some small interval delta t, and we're going to calculate the average velocity over that interval for the child, for the boat, and for the sum. So for this, we take the horizontal step to be delta t and the vertical step to be the distance. So these distances are going to be xc for child, xb for boat, and x total for the sum. Now we know that x total is xb plus xec because these two distances add to x total. So if we divide everything by the same delta t, we obtain that the velocities add. So v total is equal to vb for the boat plus vc for the child. And now all you need to do is let delta t go to 0 and you get the derivatives. So if you have three functions, f1, f2, and f1 plus f2, the derivative of f1 at a point is f1 prime of x. The derivative of f2 at that same point x is f2 prime of x. And what's the derivative of the sum? Well, since f is f1 plus f2, then f prime is f1 prime plus f2 prime. And the slope over here is going to be the sum of the slopes. And that's the sum rule. So now that you've learned the sum rule, you're ready for the product rule, which is almost the same thing except just a little bit more complicated. Imagine that you have a function f and that's the product of functions g and h. So the question is, what is the derivative of f with respect to the derivatives of g and h? Well, for this, I like to imagine a derivative as hitting the function with a hammer. So I want to hit f with a hammer, and that means I need to hit g and h with a hammer. But that's too much work. So I have to do it by parts. First, I have to hit g with a hammer and leave h alone, and then I have to hit h with a hammer and leave g alone. In other words, here's what happens. F prime is like hitting f with a hammer. And if I hit only g with a hammer and leave h alone, I have g prime h. And if I hit h with a hammer and leave g alone, I have g h prime. So the derivative of f is f prime equals g h prime plus g prime h. And that is the product rule. The way I like to imagine the product rule is by building a house. Imagine that you're building a house and you have two groups of workers, one working on the front wall and one working on the side wall. And they work at different paces, so at a given time they will have different lengths of wall built. G of t represents the length of the side wall as a function of time, and h of t represents the length of the front wall as a function of time. So what is the resulting area of the house? Well, it's the product of g of t and h of t. So let's call that f of t. F of t is the function of the area of a house with respect to time. And now we want to find the derivative of f, and we know the derivatives of g and h. In other words, we want the rate of change of the area with respect to time. So let's look at a house from the top. Now, what happens when the workers build a little bit of sidewall, delta G, and a little bit of sidewall, delta H? That also builds a little bit over here at the top. Now, let's look at what these areas are. This area over here is going to be G of t times H of t. This small area here, G of t times delta H of t. This one here is delta G of t times H of t. And this tiny one is delta G of t times delta H of t. Now the rate of change of the area with respect to time after some small time delta t is going to be delta f of t divided by delta t. What is delta f of t? Well, the change in area is this blue area over here, which is precisely the sum of the three blue rectangles. So on top we have delta G of t H of t plus G of t delta H of t plus delta G of t delta H of t, and at the bottom we have delta t. We can rewrite this in the following way. Delta gt over delta t times H of t plus delta ht over delta t times G of t plus delta g of t delta h of t divided by delta t. And now to take the derivative, we need to let delta t go to 0. So what happens with delta f of t over delta t? That becomes the derivative of f prime of t. And each one of these becomes something interesting. This one becomes g prime of t h of t. This one becomes g of t h prime of t. And this one over here becomes 0 because it's too tiny for us to care. It really doesn't make a big difference because the limit of that is 0 when delta t goes to 0. Therefore, we have the product rule. F prime of t is g prime of t times h of t plus g of t h prime of t. So now that you know the sum rule, product rule, and scalar rule, you are ready for the chain rule. It's probably the most complicated of these rules, but if you look at it from a certain angle, it can be pretty simple. Imagine that you have a function h of t, and to the output of this function, you want to apply another function g of t. So you have a composition of functions. And now you want to take the derivative of this composition of functions with respect to t. So let's say you know dh over dt, the derivative of h with respect to t. And you also know the derivative of g with respect to h. So the derivative of the composition is simply the product of these two. Now, why is it called a chain rule? Because you continue composing functions. Let's say you want to apply another function f to the output of g, and you want to take this derivative. Well, you need to know the same derivatives as before, in addition to df over dg, and the product is the desired derivative. And of course, as you can imagine, you can continue composing more and more functions, and you're just going to get more terms in the product. And that's the chain rule. Now, with the Leibniz notation, the chain rule is pretty clear. But with the Lagrange notation, there's something to keep track of because it can be a little tricky. Here it is again for two functions. Now, what is dh over dt in Lagrange notation? It's simply h prime of t. And what is dg over dh? Well, it would be lovely if it was g prime of t, but it's not g prime of t. It's g prime of whatever you put into the function g. So it's g prime of h of t. That's all you have to keep track of. It's g prime times h prime, except that you have to put the correct input in the function. So what happens with three variables? Well, the same thing. dh over dt is h prime of t. dg over dh is g prime of the input to g, which is h of t. And df over dg is f prime of the input to f, which is g of h of t. So that is the chain rule. So this is how I like to see chain rule. Imagine that you're driving your car again and you feel adventurous, so you're going to go up a mountain. The base of the mountain is pretty hot, but the top is pretty cold. So as you drive up, you notice that the temperature is changing with respect to height. And the rate of change is d capital T over dh, where capital T keeps track of temperature and h keeps track of height. But also, as time changes, you drive up the mountain. So therefore, the height changes with respect to time. And lowercase t keeps track of time, so the rate of change of height with respect to time is dh over dt. Now notice that as time passes, you drive up, and as you drive up, it gets colder. Therefore, temperature also changes with respect to time, and the rate of change is d capital T over the d lowercase t. And what the chain rule says is that you can find the third one from the first and the second. So if you know d temperature over d height and d height over d time, then their product is d temperature over d time. This is pretty much what chain rule says. But let's look at a plot to understand this deeper. We're going to plot in 3 dimensions. One axis is going to be time, the other one height, and the other one temperature. So in the bottom plane, there's the function h, which dictates how height changes with respect to temperature. And in this plane over here at the back, it's the function t that keeps track of how temperature keeps changing with respect to height. Now, as time changes a small amount delta t, then height changes a small amount delta h, and then temperature changes a small amount delta t. And the way to see it is like this. Let's say you're at this spot in time. So the bottom plot tells you that this spot in time corresponds to this height. And the top plot tells you that this height corresponds to this temperature. And if you make a small change forwards in time, then now you're at a different time spot, and that yields a higher altitude. And that higher altitude is changed by delta h, a small amount of altitude. And that delta H creates a small change delta temperature, because now it gets colder because you drove up. And so delta T implies delta H implies delta capital T. Now, these are numbers. These are very tiny numbers, delta T, delta H, and delta capital T. So this expression holds. Delta T over delta lowercase t is delta H over delta T times delta capital T over delta H. Again, these are numbers, so I can cancel delta H on top and bottom. But now, as I let delta T go to 0, delta H also goes to 0, and delta capital T goes to 0. And so this number in the left becomes dt over dt. This one over here becomes dt over dh. And this one over here becomes dh over dt. And so that's pretty much the chain rule. Welcome to week 2. In week 1, you learned everything about functions with one variable. Now you're going to learn everything about functions with 2 or more variables. So for example, things like a tangent line in 1 dimension will generalize to a tangent plane in 2 dimensions. This can also be used in optimization in the exact same way, and it also applies to machine learning in the same way. However, optimizing functions in 2 or more variables can get very complicated even for a computer. So we're going to introduce methods that will speed this up. One method that we'll learn is called gradient descent. Then I will show you how to use gradient descent to optimize several functions. But for now, let's start with a very important concept, the tangent plane. So in week 1, you learned about derivatives of functions in one variable. For example, this one, f of x equals x squared, which is a parabola. And visually, you could identify the derivative at each point as the slope of the tangent line at the point. For example, at the point 2, 4, the slope of the tangent is 4. So the tangent is this one over here. Now, what happens if we have a function of 2 variables? Well, let's think of a simple one. Let's think of f of x, y equals x squared plus y squared. So now the function has 2 inputs and 1 output. Therefore, it needs to be plotted in 3 dimensions. So we're going to plot it over here. X and y are the 2 horizontal axes in the floor, and z, or f of xy, is plotted as the height. And now the tangents are not lines, they're planes, like this plane over here. So that is called the tangent plane. So how do we get this tangent plane? Well, essentially it's the same as the 1D case, except we have to take 2 cases. We have to actually cut the space into planes and then calculate the tangents on these planes. So let's say we fix y equals 4. That means we're cutting the space here, and we have a parabola, the red parabola. Now let's cut the space with x equals 2. So now we have another red parabola, and in this parabola we can find a tangent line. So once we have the 2 tangent lines, then we have a plane, because any 2 lines that cross actually represent a unique plane. So that one over there is the tangent plane. So what were the calculations we did here? Well, when we fixed y equals 4, then we cut the space with a slice, and we also let y equals 4. So that's why this function f of x4 became x squared plus 4 squared, because y is 4. And that function is easy to differentiate with respect to x. The derivative is 2x, so that's the slope of one of the lines. And when we fixed x equals 2 is when we slide the space with the other direction. So now you get the function f of 2 y, which is 2 squared plus y squared, by replacing x equals 2, and you can differentiate that with respect to y. You get 2y. Now, if these calculations seem confusing, don't worry. We're gonna elaborate them a little more over the next few videos. Before we get to partial derivatives, I want you to have the following mental picture. Imagine that you have this function of 2 variables plotted in 3D space, and that you cut it with a plane like this. What do you get? You get something like this. And in the cut, you can see this red parabola with a tangent over there. That's the partial derivative. Now you can also cut it in another direction. You can cut it like this. And then you get also a red parabola, and that red parabola is a function of one variable, so you can draw tangents like the black tangent over there. So let me elaborate a little more. If we take our function in the variables x and y, which is plot in 3D, and let's say we fix a value of y. In this case it's 4, but it can be anything. So we treat y as a constant. All of a sudden, if you treat y as a constant, this is no longer a function of two variables. It's now a function of only one variable, represented by this red parabola over here. Now, let's take some point in that red parabola and let's draw a tangent like it's drawn here, that black line. What is the slope of this line? The slope of this line is the partial derivative. So how do we calculate a partial derivative? Well, it's very simple. Let's take the formula for the function. F of xy equals x squared plus y squared. Since we fixed y, and it doesn't really matter what value we fixed it to, we are treating y as a constant. So when you differentiate this function, now this function is only a function of x. So when you take the derivative with respect to x, which we're going to call di f over di y, where di is this symbol over here, that's partial derivative, then it's going to be 2x, which is the derivative of x squared with respect to x, plus 0, because 0 is the derivative of a constant. Remember that y squared is now a constant, so its derivative with respect to x is 0. So therefore, the slope of this line over here is 2x. So you can take two partial derivatives with respect to x and with respect to y. So what happens when we treat y as a constant? Well, the partial derivative is 2x. And if we were to treat x as a constant, then the partial derivative is 2y, because the derivative of x squared is 0 and the derivative of y squared is 2y. In other words, if you have a function f of x comma y, you can take two partial derivatives. There's two ways to denote it. One is f sub x, and the other one is di f over di x. And you can also take the partial derivative with respect to y, and that's fy or di f over di y. So these two are the two partial derivatives you can take of this function. And as you can imagine, if I have a function not of two variables, but of, let's say, 10 variables, then I can take 10 partial derivatives, one with respect to each of the variables. Now, if those calculations weren't super clear, let me do them in detail here. So let's say you have the function f of x comma y equals x squared plus y squared, and the task is to find the partial derivative of x with respect to x and y. So let's do di f over di x first. We're going to try to find these two. And as I said before, that's the partial derivative notation over here. So when you want to find the partial derivative of f with respect to x, there are two steps. The first step is to treat all the variables as constants. So in this case, y is the other variable, so we're going to treat y as a constant. And step 2 says, differentiate the function using the normal rules of differentiation. So let's start. This y squared over here is a constant, so it might as well be a 1. We can think of this as f of x comma y equals x squared plus 1, because the derivative of 1 is 0, because it's a constant. So di f over di x is simply 2x, because that's the derivative of x squared. And what's di f over di y? Well, now x is the one that behaves as a constant. So we can think of this as 1 plus y squared, or 7 plus y squared, or anything you want. And the derivative of 1 plus y squared with respect to y is 2y. So those are the partial derivatives. So in order to really nail down the concept of a partial derivative, let's do one more example. Let's say that the function now is f of xy equals 3x squared times y cubed. So the task is to find the partial derivative of f with respect to x. So in the following quiz, calculate the partial derivative of f with respect to x, or di f over di x. So the way to do this is with the two previous steps that we learned. Step 1 is treat all the other variables as constants. So in this case is the variable y. That means this y cubed is a constant. So we're going to cover it with a box to remember that it's a constant. Step 2 says differentiate the function using the normal rules of differentiation. So how do we do this? Well, this 3 is a constant, so if you remember the multiplication by scalar rule, we put this constant here, and that will multiply the derivative. The next factor is x squared. So what's the derivative of x squared with respect to x? It's simply 2x. And finally, this gray box is another constant, so it multiplies in the derivative as the same constant. Now you remember that the gray box was y cubed. So all of a sudden we have the derivative. It's 3 times 2x times y cubed. Simplifying, it's 6xy cubed. And that's the partial derivative. Now let's do the other one. What is the partial derivative of f with respect to y? That's what the next quiz is about. So for this one, you do the exact same thing, except now you have to treat the x as a constant because you're taking the derivative with respect to y. So let's cover x squared with a box to remember that it's a constant. And now let's take the derivative just like before. 3 is a constant, so it goes here. Then the constant is a constant, so it goes here. And then the derivative of y cubed is 3y squared. So now you remember that the constant was an x squared all along. So the derivative is 3x squared times 3y squared, which is 9x squared y squared. And that is the partial derivative of f with respect to y. In this video, I'm going to show you a nice way to condense all the partial derivatives into a vector known as the gradient. And I'm going to show you what notation is used for the gradient. So now that you know what a partial derivative is, you pretty much know what a gradient is. So recall that if you have a function in 2 variables, you can slice it in 2 ways. Treating y as a constant and treating x as a constant. Each one gives you a different partial derivative. The first one gives you the partial derivative df over dx, which is 2x. And the second one gives you the partial derivative df over dy, which is 2y. And so the gradient is simply the vector containing these 2 partial derivatives. So basically the vector 2x to y. In general, we call the vector using the nabla letter, nabla f, and that's just a collection of all the partial derivatives with respect to all the variables in the function. So in this case, it's a vector of 2 entries because the function has 2 variables, but if the function had 17 variables, it would simply be a vector of 17 entries, each one corresponding to the partial derivative of the function with respect to each one of the variables. So this gradient, in this case 2x to y, is a pretty good description of the tangent plane because it describes the slopes of the 2 lines that form that tangent plane. So now let's do a small exercise. Please find the gradient of f of xy at the point 2, 3. And feel free to think about it. And the answer is nabla f equals 2x to y, except for x and y, you replace 2 and 3. So this is 2 times 2 and 2 times 3, which is the vector 4, 6. So that is the gradient of the function f of xy equals x squared plus y squared at the point 2, 3. So in this video, I'm going to show you something very interesting. The gradient is pretty useful to minimize functions of 2 or more variables in the same way as the derivative was useful to minimize functions of 1 variable. So let's go back to a function of 1 variable, this parabola f of x equals x squared. And now let's look at the function we've been studying in 2 variables, which is f of xy equals x squared plus y squared. Now let's go back to the function of 1 variable. When you want to minimize this function, the minimum point is this point over here. And the way to find it is to find the point in which the slope is equal to 0. So we take the derivative, solve that derivative equals 0, and the solution is this minimum point over here at 0. So what happens with more variables? Well, something very similar. The minimum point is this point over here. And notice that the tangent plane is actually parallel to the floor. And that's going to happen in every local minimum and maximum, that the plane is parallel to the floor. Now, since we're not dealing with planes, but we're dealing with partial derivatives, let's actually draw the two partial derivatives. Notice that they are these two lines over here, and both have slopes of 0 because they're parallel to the floor. So in other words, the minimum of the function f on the right happens when both of the slopes of the tangent lines given by the partial derivatives are 0. And if you have a function of many more variables, say a function of 12 variables, then you're just going to need for 12 slopes to be 0, those corresponding to all the partial derivatives. So now let's do a little bit of math. On the left, you want to solve the slope equals 0, so the derivative equals 0. That means you want to solve for f prime of x equals 0. Now f prime of x for x squared is 2x, because that's the derivative of x squared. And when you solve for 2x equals 0, you're basically getting the solution x equals 0. And x equals 0 is precisely this point over here. Now what happens when we do this in more variables? Well, you want the two partial derivatives to be 0. That means df over dx and df over dy are both 0. Now what's df over dx? That's 2x, and df over dy is 2y. So you want 2x equals 0 and 2y equals 0. That's the same as the point x comma y equals 0, 0, which is this point over here. Now, this time, solving the system of equations 2x equals 0 and 2y equals 0 was pretty easy to get the point x, y equals 0. Sometimes you may have to do a little bit of work, but basically, to find the minimums and maximums, all you have to do is set all the partial derivatives to 0 and solve that system of equations. Now that you've learned how derivatives work in more than one dimension, I'm going to show you how to use them in optimization. And the example we're going to use is the same one we used before of the sauna, except now the sauna has 2 dimensions. So in week 1, you saw a simple example where you were in a sauna and wanted to get to the coolest point since you were starting to feel hot. But in this simple example, you were in the bench in the sauna and you could only move in 2 directions, to the left and to the right. Now let's look at a more realistic scenario where you can move in any direction because you're standing anywhere in this room. So it's a 2-dimensional sauna. Now, let's consider that the sauna is this 5x5 room. And you're standing here, but you can walk in pretty much any direction that you want. And again, you're starting to feel hot, so you want to get to the coldest place in the room. And the temperature looks like this. The red points are hot and the blue points are cold. And for each position x, y, where x and y are the 2 coordinates, the temperature is the value of the function at that point, which is represented by the height. So the red points are high because they represent hot points, and the blue points are low because they represent cold points. And the goal is to find that coldest place, that blue point over there at the right. So first, let's try the same approach you did on week 1 to get to the minimum. Let's say that you're standing over here and you're going to basically move around a little bit and see where does it get colder. So let's say you want to take a step in this direction and in this direction and in this direction, and from those you select which one was colder. So clearly it's the blue direction, so let's move 1 step here. And now let's iterate. Let's continue doing that and moving in some random steps and checking out those steps, which one took us to a colder place, and continue doing this. So it's believable that if you do this for a while, you will be able to take steps that take you to the coldest place in the room. And how do you recognize the coldest place in the room? Well, just like before, it's a place where if you walk in any direction, you get hotter. There's no way to get colder by taking a step in any direction. Another way to look at it is if you were to take the tangent plane to the temperature function, this tangent plane is parallel to the floor because the 2 derivatives, the 2 partial derivatives, are both 0. And these are given by di t over di x and di t over di y, where t is the temperature function and x and y are the two coordinates in the sauna. So let's put some numbers here and see how things go. Let's say that the temperature is this function 85 minus 1 over 90 times x squared times x minus 6 times y squared times y minus 6. So it's a little more complicated than the previous one we had of x squared plus y squared, but the math is very similar. So here is an exercise. Given this function, try to calculate the partial derivatives di f over di x and di f over di y. I encourage you to pause the video and take pen and paper and try to calculate them. And I will give you the answers. The answers are di f over di x is minus 1 over 90 times x times 3x minus 12 times y squared times y minus 6. That's the one you obtain by letting y behave as a constant. And di f over di y is minus 1 over 90 times x squared times x minus 6 times y times 3y minus 12. Those two are the partial derivatives. Now, to find that minimum point, remember that you have to set them both equal 0 and then solve for x and y. Now, this is going to give us a lot of points. And many of them won't be the minimum. Only one of them will be. So we have to go through this slightly tedious approach of looking at all the pairs x, y for which these two partial derivatives are 0. But that can be done. Take a look at di f over di x. It's a product of several things. And for a product of several things to be 0, one of them at least has to be 0. So the possibilities here are that x is equal to 0, or that 3x minus 12 is equal to 0, in which case x is equal to 4, or that y squared is equal to 0, in which case y is equal to 0, or that y minus 6 is equal to 0, in which case y equals 6. And similarly for di f over di y, either x is equal to 0, or x is equal to 6, or y is equal to 0, or 3y minus 12 is equal to 0, in which case y equals 4. So let's put all these candidates together. So for these candidates, if x is equal to 0 or y is equal to 0, then you have one point where the gradient is 0. And the other points are all denoted over here. So notice that some points are outside of the sauna, so we don't care about those. Now, for x equals 0 or y equals 0, those are all maximum because as you can see, all these points give 85 as the temperature. So those are not the minima. The only minimum is this one over here, x equals 4, y equals 4, which is the point we were looking for. For this point, the temperature is 73.6. So this is the minimum. So as you can see, just like we did for one variable, you set the derivative equal to 0. That gives you a bunch of candidates and then you check them individually. Over here, we simply set both derivatives equal to 0 and get a lot of candidates and then check them individually. In this video, we're going to go back to the power line example from a previous lesson. However, this time, the example is in 2 dimensions instead of 1. The reason I really like this example is because it introduces one of the most important machine learning models out there called linear regression. And then you're going to see how to solve a linear regression problem using optimization. So in a previous lesson, you saw a power line problem in 1 dimension where you need to determine where to place your house in order to connect to 3 power lines with the least cost. In this lesson, we work with a similar problem, but in 2 dimensions. So now the power lines have coordinates and they're going to be located on an XY plane like this one. So here are the 3 positions of the power lines. And the problem is the following. You now want to find the optimal place for a fiber line connection that goes in a straight line in such a way that you reduce the total cost of connecting to the 3 power lines. And how do you connect to the power lines? You can connect to each power line by connecting a wire to touch the fiber line, but the wire needs to be parallel to the y-axis. And the cost for connection is the square of the length of the wires, just like before. So here are the 3 connections and the 3 costs. So the costs are the area of the 3 squared, and the total cost is the sum of these areas. Now, the point is to find the perfect line that reduces this cost and minimizes it. And that becomes a mathematical problem, because if you look at the line can have an equation such as y equals mx plus b, where m is the slope and b is the y-intercept. And the goal is to find the optimal m and b to minimize the sum of squares. Now, before we had a function with x and y, now we have a function with m and b, but it's the same thing. We're minimizing a function of 2 variables. The function is the sum of the areas, and the 2 variables are m and b. So let's actually calculate the function that we want to minimize. So focus your attention on the blue square. Now the blue power line is located on the coordinate 1, 2, and it needs to connect to the fiber line. Where does it connect? In the point 1, m plus b. Why is that the point 1, m plus b? Because if we let x equals 1, then mx plus b is equal to m plus b. So the y-coordinate of the point of connection is m plus b, and the y-coordinate of the power line is 2. Therefore, the distance is m plus b minus 2, and the cost is m plus b minus 2 squared. In a similar way, the cost for the yellow power line is 2m plus b minus 5 squared, and for the green power line is 3m plus b minus 3 squared. And therefore, the total cost is the sum of these 3 numbers. Now let's expand this. The first one, m plus b minus 2 squared, expands as this. The second one expands as this, and the third one expands as this. And if we join similar terms, we get that e of mb is 14m squared plus 3b squared plus 38 plus 12mb minus 42m minus 20b. And that is the cost function that we want to minimize. So we want to find the m and b that make this expression e of mb the minimum. But we know how to do this already. All we have to do is calculate the 2 partial derivatives, di e over di m and di e over di b, set them both equal to 0, and then solve for m and b. So let's start with a quiz. Please help me find the partial derivative of e with respect to m. And the answer is 28m plus 12b minus 42. Now let's do another quiz. Help me find the partial derivative of e with respect to b. And the answer is 6b plus 12m minus 20. So now that you have these 2 partial derivatives, all you have to do is set them to be equal to 0 and solve for m and b. You know how to do this from the linear algebra class. So let's actually work it out. And once we work it out, that m and b are going to be the optimal values to minimize e of mb, and they're going to give us the perfect line. So how do we solve this? Well, let's start with the second equation, and let's multiply it by 2 to get 12b plus 24m minus 40 equals 0. Now let's subtract it from the first equation to get 4m minus 2 equals 0. This is equivalent to m equals 2/4, which is 0.5 or 1/2. Now let's take that m equals 1/2 and plug it back into the second equation to get 6b plus 12 times 0.5 minus 20 equals 0, or 6b plus 6 minus 20 equals 0, or 6b minus 14 equals 0, which gives us the solution b equals 14 over 6, or 7 over 3. If this seemed a little confusing, please check the linear algebra class where this is explained in detail. So now we have the solution to the system. The solution to the system is m equals 1/2 and b equals 7 over 3. Those are the 2 values that make those 2 partial derivatives 0. And if you plug them back to the equation, you get that e of 1/2 7/3 is 4.1. 0.167. That is the minimum value of the cost. And let's see how this looks in the graph. If you plot the line of equation 1/2 x plus 7/3, you get this line over here. And notice that indeed, this line gives some pretty small squares. So that's it. That's how you minimize the square loss. This problem is actually called linear regression. Linear regression is a very, very important problem in machine learning where you have a bunch of points and you try to find the closest line to them. And that's exactly what we did here. Now, notice one problem here. When we solve this equation of 2 variables and 2 unknowns, that can be pretty hard, especially if you were to have many variables. Solving an m by n system of equations can be pretty expensive. Is there a faster way to do it? So the answer is yes, and you're going to see it next in the class. It's a method called gradient descent, which actually helps minimize functions in a pretty fast way. So stay tuned for the next few videos where you're going to learn gradient descent. So far you've learned how to solve optimization problems using derivatives and gradients. However, when you try to get exact solutions to these problems analytically, you're going to start noticing that these problems can get really complicated really fast, especially in higher dimensions. In this lesson, I'm going to show you a method that is iterative and that is really powerful for minimizing or maximizing functions, especially in many variables. The method is called gradient descent. But let's start with gradient descent in one variable in order to work our way up to gradient descent in several variables. So let's look at the following function. F of x equals e to the x minus logarithm of x. This is the plot of the function, so it's nice and smooth. And the question is, can we find the minimum here? And the minimum is somewhere around here. And we know how to do it from previous lessons. All we have to do is calculate f prime of x and set it equal to 0. And then solve for x. So what is the derivative of f of x? It's e to the x minus 1 over x. And the reason is because the derivative of e to the x is e to the x, and the derivative of logarithm is 1 over x. So all we have to do is solve for e to the x minus 1 over x equals 0. However, this is pretty challenging. Let me show you. Solving for e to the x minus 1 over x equals 0 is equivalent to solving for e to the x equals 1 over x. And I challenge you to try. It's actually pretty hard to do analytically. The solution is 0.5671, etc., which is a famous number. It's known as the omega constant. However, the fact that this is really hard to solve analytically should not stop us from trying something. The question is there any other way? So here is one method. Let's pick some random value. Let's say somewhere around here. And now let's give it a try and move to the left by a little bit and move to the right by a little bit. And now we have 2 new points to try. Which of these 2 points is better? Well, since we're trying to minimize the function, let's go for the one on the right, which has a smaller value in the function. So now we are at this point, and let's repeat. So we move in both directions and check to see which point is smaller. And this one wins. So let's try it one more time. We move in both directions, and now something interesting happens, which is that both points on the 2 sides have a higher value. So therefore, let's settle for this point. And we say that this point, well, it may not be the minimum, but it's close enough to the minimum. Now this method is not bad, but we can actually improve it a lot to get really, really, really close to the minimum. Let me show you in the next video. In the previous video, we learned an okay way to approximate the minimum of a function. However, here we're going to try something smarter. So let's say you're over here and you want to get closer to the minimum. What would you tell this point to do? You would tell it to step to the right a small amount. What if the point is over here? Well, you would tell it to step to the left. Now, is there any information on the function that could help you make this decision quickly? Well, let's look at the derivative. Over here, the slope is negative and you're moving to the right. And over here, the slope is positive and you're moving to the left. So that's the information you need. you actually need to subtract the slope, because if you are at a point where the slope is negative, you need to add a little bit to the coordinate of the point. Whereas if you're in a place where the slope is positive, then you need to subtract a little bit to the coordinate of the point. So in short, if you want a new point that is closer to the minimum, then that should be the old point minus the slope. Why? Because if you're to the left of the minimum, the slope is negative, so you're subtracting a negative number and moving to the right. And if you're to the right of the minimum, then you subtract a positive number, the slope, and move to the left. Now, if the new point is x1 and the old point is x0, then the formula is x1 equals x0 minus f prime of x0, which is the slope. However, there's a small caveat. Imagine that you're over here at a very steep part of the curve. Because the function is steep, then the derivative is very large, so you're making a really long jump. Now, long jumps can be pretty chaotic, and the reason is because you may actually miss the minimum and go pretty far away and get lost. We want to take small steps and be more secure in our path. So how do we take into account a small step? Well, you simply modify the formula and put a small number multiplying the slope, for example 0.01. You can take any small number you like, and that's called the learning rate and is denoted alpha. There's a whole science in picking good learning rates. Now, this formula has an added bonus. Imagine if you're over here far away from the local minimum and in a steep part of the curve. You would be taking a big step, obviously not big because you don't want to miss the point and go too far, but relatively big. However, if you're really close to the minimum, in a part that's more flat, you want to take a small step. Now, this is included here in the formula, because if you're in a steep part of the curve, the derivative is big and you're taking a large step. However, if you're in a flat land, then the derivative is small and you're taking a small step. So imagine like in golf, if you're far away from the hole, you want to hit it really hard to get there closer. But if you're really close to it, you want to hit it with precision, so not a lot of strength. This method is called gradient descent, and it's really, really useful in machine learning, and that's why it's so popular. And it only consists in iterating this procedure. So you start with x0, and from x0 you can get a point x1 using the formula. Then you can get another point x2 based on x1 by just plugging x1 in the formula now. And you can continue. You can iterate it many times, 20 times, 100 times, thousands of times. This is a pretty fast algorithm, so it can be iterated thousands of times quickly. And its results are amazing. It can get us really, really close to the minimums of functions. And that's why it's so widely used in machine learning. So here is the algorithm in short. You start with a function f of x, and the goal is to find the minimum of f of x. So first you define a learning rate, and you choose a starting point. And then you do the updating step, which is xk equals xk minus 1 minus alpha times the derivative at xk minus 1. And then you repeat this step until you're close enough to the true minimum. You can tell that you're close enough to the true minimum when your steps don't really change that much. So now let's try it on the example. Let's do a couple of iterations. Recall that the function is e to the x minus logarithm of x, and the derivative is e to the x minus 1 over x. So let's pick a starting point of 0.05 and a learning rate of 0.005. So the first iteration is we find the derivative and we move by learning rate times derivative. So we get a new point, 1.1447, which is closer to the minimum. And then we take another iteration. We find the derivative and subtract learning rate times derivative to get 0.1735. And then we can repeat many times until we get pretty close to the minimum. Notice something interesting, which is that in this algorithm, you never needed to solve e to the x minus 1 over x equals 0. You never need to solve for the derivative equals 0. You only need to know the derivative and then apply it in the algorithm when you're taking the updating step. So that's a huge improvement. In the previous video, you learned the learning rate. Learning rate is a big deal in machine learning, and finding a good learning rate can be pretty hard. And it can also be pretty influential to how well your model does. Let's say you have a learning rate that's too large. Well, then you may miss the minimum and never be able to find it because your steps are just too big. What if the learning rate is too small? Well, then you may take forever to actually reach the minimum or perhaps never reach it. What you want is a learning rate that is just right. However, finding a learning rate that is just right can be pretty hard. It's actually a research problem to find a good learning rate. There are a lot of really good methods that change the learning rate based on how the problem is doing, but there's no definite method to find a good learning rate. Now here's another problem that gradient descent may have. Let's say that you have this function over here. So the minimum is actually this one. However, let's say that you start running your gradient descent algorithm over here. Well, it's never going to take you to that minimum because it takes you to what's a local minima. It's a point that looks like a minimum, but it's not. So how do you overcome this problem? Well, there's actually no secure way to overcome it, but a way to get pretty good results is to run the gradient descent algorithm many times with many different starting points. And once you run it with these, well, chances are one of them will get you to the minimum, or at least to a pretty good point. Now that you learned gradient descent for one variable, let's learn it for more variables. We're going to start in the bottom and work our way up to the complete gradient descent algorithm. Now earlier this week, you used an example of temperature in a sauna to introduce optimization with two variables. The goal was to move from your initial starting point to the coolest place in the room. Now in the previous lesson, you learned how to solve a problem analytically by calculating the partial derivatives and equating them to zero. The goal now is to find some alternative way to solve this problem using gradients, just as you did in the previous video for a one variable function. So let's say that you start here in the sauna and you're going to take some random steps. So you take 4 random steps in 4 directions and you're going to see which one of the 4 gets you to the coldest place. So let's say it's this one. So you move a step in that direction. Now again, you take 4 random steps and see which one of the 4 takes you to a coldest place, and you take that step. And you can iterate. You can continue doing this until you get either to the coldest place or at least somewhere close to the coldest place. However, there's some small caveats. How do you pick the directions in which to take steps? Is there any smart way to take these directions? Well, just like in the previous video with one variable, there is a smart way to do it, and it is using derivatives, except this time it's going to be using gradients. So again, in the previous video, you saw an okay way to take you closer to the coldest place in the sauna. However, there was a lot of random steps in that algorithm, so we're going to do it more exactly and more mathematically. Just like we did before with one variable, we're going to define gradient descent in 2 variables. So it's very similar. You start with an initial position, except now the initial position has 2 coordinates, x0 and y0. And before you used to draw the tangent or the derivative, but now we're in 2 variables, so we have 2 tangents. This one over here, and notice that it's pretty steep. We're going to draw that magnitude in the floor in the direction that the derivative is increasing. So because it's steep, it's a big vector. And now we're going to do the same thing with the other component of the gradient. So we get a smaller vector on the floor because this second gradient is much flatter than the previous one. Now let's take the sum of these 2 vectors, or the vector with the 2 coordinates, and that is the gradient. Now the gradient has an interesting peculiarity. It's the direction of greatest ascent. So if you want to take a small step and get to the hottest place you can on a small step, you want to take in the direction of the gradient. But we don't want to get hotter, we want to get colder. So we take it in the direction of the negative gradient. And the direction of the negative gradient is the direction that if you take 1 step, takes you to the coldest possible place that you can get to in 1 tiny step. So we're going to take that step in the direction of the negative gradient. And it's going to be a small step, so we multiply by the learning rate again. And so we get x0, y0 minus learning rate times gradient, and that's our new point x1, y1, and that's a better point. So notice that this is exactly the same as gradient descent in one variable, except instead of the derivative, we simply take the gradient. So now let's see how this works for the previous example. This is the formula for the temperature. It's 85 minus 1 over 90 x squared times x minus 6 times y squared times y minus 6. And let's run a couple of steps of the gradient descent algorithm. Let's start with the point 0.5, 0.6. Now we have to calculate the gradient, which is the partial derivative with respect to x and the partial derivative with respect to y put together in a vector. We've already calculated these derivatives previously, so here they are. And all we need to do to find the gradient is to put them together in a vector. Now, let's plug x equals 0.5 and y equals 0.6 into this vector to get the gradient over here at this point. And now, simply take a step. You move in the direction of the gradient times the learning rate with a learning rate of 0.05. That gives you a new point. It's not 0.5, 0.6 anymore. Now it's 0.5057 and 0.6047. So you move in that direction. Now you're just a little bit closer to the minimum point. And now let's run this algorithm again. So we calculate the gradient and we move in the direction of that gradient. So we get a new point. And you simply repeat this many times. And if you repeat this many times, then you are going to get really close to the minimum really fast. So in short, the gradient descent algorithm is very similar to the one we did in one variable. Now we have a function f of x, y. The goal is to find the minimum. So the first step is to define a learning rate alpha and to choose a starting point x0, y0. Step 2 is to update the kth position by taking the kth minus first position and subtracting the learning rate times the gradient at the k minus first position. And then step 3 says repeat step 2 until you're close enough to the true minimum. And as usual, you know when the true minimum is happening because it's when you move really slowly, or maybe not move basically at all. So now, just like gradient descent in one variable, gradient descent in two or more variables still has the same drawbacks. For example, you want to get to this global minimum, but you may accidentally get into these local minimums over here. And the way to overcome this, at least with high probability, is to start at very different places. Notice that here we start at 3 different places, and each one of them took us to a different local minimum, with one actually reaching the global minimum. But just like with one variable, there's no way to tell for sure if you got to a global minimum. But if you run it many times, probably what you got as the optimal solution is pretty good. You may remember from earlier this week that you solved a linear regression problem using power lines. But even with 2 variables and a simple problem, this turned out to be pretty cumbersome. In this video, I'm going to show you how to solve the exact same problem using gradient descent, and you're going to see how fast and easy it is. So the power lines example was the following. You wanted to try to find a best fiber line that reduces the cost of connecting to the power lines. And the problem boiled down to minimizing this function, so finding the optimal m and b that will find the smallest value for e of m and b. And analytically, you found that it was 1/2 and 7/3, and it gave a value of 4.167. However, we can also do this using gradient descent. The idea is to minimize the sum of squares cost, and this was the gradient. So all you need to do is find the optimal m and b. For this, you have to first start at some initial starting point, and then the points mb such that the cost is minimum is over here. So what you do is you take tiny steps descending until you find the minimum. Mathematically, the steps are the following. First, you start with some point m0, b0. That's some random slope and some random y-intercept. And then you iterate mk plus 1 bk plus 1 is the k plus 1th iteration, and that's the kth iteration minus alpha times that gradient on top evaluated at mk bk. So let's take a look at the power line problem again. Here are the 3 power lines, and here is the line that tries to fit them really close. The equation is y equals mx plus b. Now we're going to relate that to this plot at the right. The plot at the right is the cost of the power lines. Let me show you how. Over here, we're calculating the areas of the squares, and recall that the sum of these areas was the cost of that fiber line. Now let's say that this was a numerical value given by this segment. So what's going to happen is that the plot on the right is going to measure the square loss here in the vertical axis. The way it's going to do it is the following. This line is parameterized by the slope and the y-intercept m and b. So let's put m and b in the two axes here in the floor. Now, in the point mb, we're going to plot the height of the cost function. And this point over here is going to be corresponding to the line on the left. Now, this is a pretty good line fit, so it's going to have a small error. Let's look at another point. Let's look at an awful line. This one doesn't fit the points really well because it has a really high loss, and therefore is going to be at a point over here in the error function plot. And the idea is the following. In the plot on the right, you're going to use gradient descent to get to the very bottom and to be able to minimize the cost function. And as you do that, you're going to be changing m and b. And as you change m and b, then the plot on the left is going to have a better line fit. And that's how you solve linear regression, using gradient descent. Now let's see another example, one related to advertising. Let's say that you work in an agency and you have a TV advertising budget, and that relates to number of sales. And of course, if you increase the budget, the number of sales increases, and if you decrease the budget, the number of sales decreases. And you would like to be able to predict the number of sales given a certain advertisement budget. So you start looking at your data, and the goal would be to predict the sales in terms of the TV budget. And the first tool you would try to use is linear regression. In other words, try to find a line y equals mx plus b such that if you plug in x, the TV budget, then you get y, or at least something pretty close. The idea is that you have a lot of observations. So let me show you how to do gradient descent with a lot of observations. So let's go back to a plot, and let's say the TV budget is in the horizontal axis and number of sales in the vertical axis. And you have a bunch of points, let's say n of them. Here you have x1, y1, x2, y2, up to xn, yn. So let's calculate the cost function. Let's look only at the first point, x1, y1. What is the cost at that point? Well, is this length squared. Now, what is this length? Well, the point on the line has the form x1, mx1 plus b, and the reason is that the x-coordinate should be the same as in x1, y1. So what is that distance? Well, it's simply y1 minus mx1 plus b. Or we can also write it as mx1 plus b minus y1, because at the end of the day, we're going to be squaring it, so it doesn't really matter if it's negative or positive. So when we square it, we get the loss at that point. Now, we're going to add all the losses of all the points. And let's actually take the average. So we divide it by m. And there's an extra 2 there. And the reason that 2 is there is that when we take the derivative, the 2 in the exponent cancels with this one. But it doesn't really matter. There could be a 2 there or not. Because if we multiply the function by 2 or divide it by 2, the minimum point is still going to be at the same m and b. So our total cost function is L of m and b given by this average of all the losses. And now all we're going to do is gradient descent. We start at a point m0, b0 that gives us some random line that may or may not be a good fit. And then using that, we calculate the next iteration, m1, b1, which is m0, b0 minus the learning rate times the loss. That gives us a slightly better line. And now we can iterate. We can now find m2, b2 using the same thing except plugging m1, b1, and then m3, b3, and do it many times. Let's say we do it capital N times until we get a pretty good fit. And that's the formal version of the gradient descent algorithm. Welcome to week 3. In this week, you're going to learn what a neural network is and how to train them using gradient descent. You're also going to learn an alternate method to gradient descent called Newton's method, which is also very fast and very useful. But let's start with the first video. In this video, you're going to learn the fundamental unit of neural networks called a perceptron. That may sound like a foreign term to you, but you've actually seen one already, because linear regression can be expressed as a perceptron. So let's start with the motivation behind our regression problem. We'll be using one of the most classical examples used in linear regression, predicting the price of a house given the size of the house. So let's say you have data on 3 houses. The first one has 1,000 square feet and it costs $20,000. The second one, 2,000 square feet and a cost of $30,000. And the third house has a size of 3,000 square feet and costs $50,000. And let's say that you have more data points which you plot on this graph. So these are other houses on the market with their sizes and their prices. And the goal is to take this data of inputs, which is the size of the house, and find, in this case, a line, because they look like they form some sort of a line. So we're going to find a line used to predict the price of the house. And the goal is to find the best possible line. Now, in this case, we only have one input type, which is a feature that we're going to use to predict the prices. What if we threw in a second feature? So let's throw in another feature. Let's say the number of rooms. Now the houses have 2, 4, and 7 rooms respectively. With this added feature, the problem is not so simple anymore, and we need to consider how both features affect the output. Then how do we build and train a model that is able to make predictions of the house prices? And more. What if we had more features? What if we have like 10 features or 100 features? Well, here's where the perceptron comes in. So this regression problem can be modeled with a single perceptron. The perceptron is going to take some inputs into some unknown outputs that we want to predict. So first, we're going to start by exploring the perceptron mathematically. So let's start with the inputs. The inputs here are going to be x1 and x2 corresponding to the size of a house and number of rooms. But I want you to imagine this if there were 100 inputs. It would simply be 100 nodes, x1 all the way to x100. So we start with the inputs and then they plug into a summation function. I'll explain more about this in a little bit. Out of the summation function comes the output y hat. And that's going to be what we predict to be the price of the house. So a good model will come out with pretty good predictions. And the idea is to build the best possible model. So what is happening in this summation step? Let me do it more in detail. Each of these features, x1 and x2, is multiplied by a corresponding weight to determine how important it is for the output. So for example, if the size of a house is way more important to predict the price of a house than the number of rooms, then this will have a higher weight than the number of rooms. So let's call the corresponding weights W1 and W2. And to combine these weights and the input, we simply add them. So we multiply W1, the weight, times x1, the feature, and we add W2 times x2. And we're almost there. We're not quite done because there's also a bias term that gets added to the summation function. And now we add this, and that is the output. In this model, there's no activation function. I will tell you later what an activation function is. But here, the output is simply y hat. That's w1x1 plus w2x2 plus b. That's the predicted price of the house. And the goal is to find the best w1, w2, and b, the weights and bias, that will optimize the predictions. So the ones that will, when we plug in x1 and x2, give us the closest to the actual price for the entire data set. Now, how do we do this? How do we find these perfect weights? The idea is that we want to minimize some kind of error. The error is basically how far are you from the price of the house. And so if you minimize that error, then that's all we need. So for that, we introduce something called the loss function. The loss function is a little function that's going to tell us how far are we from predicting the prices well. So that's on the next video. So in the previous video, you saw a data set with a bunch of houses and their prices and also their sizes in square feet. So the idea was to fit the best possible line to these points. So the line that passes the closest possible to these points. And that would be what makes a good prediction. So this line over here is precisely the model, and we need to find a way to evaluate the model to see how well it's doing, and based on that to see how can we improve it to get a better one. So first, let's see what the model predicts. So the model predicts this column. How? Well, the point corresponding to the first house is at height 15,000, and the one corresponding for the second house is at height 30,000, and for the first one is at 45,000. So this looks like a pretty good model. We may be able to do better, but this so far looks like a pretty good model. At least you can see it correctly predicted the price of the second house, and it was not so far from the first and the third. But let's quantify how far it was. By that, we need to subtract the predictions from the actual value, and we're going to call that the error. And that error is indicated by these vertical broken lines over here. So clearly, the shorter the line, the better the model, because that means the predictions are close to the actual values. However, there's a small problem with y minus y hat. If the point is above the line, then this is positive, and if the point is below the line, then this is negative. And a negative error is also bad, as well as a positive error, but if we add them, we can get 0 or small numbers, so this can get confusing. So for that, we square the error. Y minus y hat squared is the actual measure that we want. And in machine learning, we actually multiply it by a half. And the reason is really more cosmetic, because in reality, when you take the derivative of y minus y hat squared, then you get a lingering 2. So we put a 1/2 there to cancel with that 2, and then we have less numbers to keep track on. But at the end of the day, you can multiply this error by any constant you want, and you still don't change anything at the end. So now we have a prediction function that outputs some kind of prediction y and is given by this formula. And the loss function we're going to call L, and for every point is 1/2 times y minus y hat squared. So it's the distance between the prediction and the value squared multiplied by a half, and we're going to call that L of y hat. And our goal now is to minimize this. So to find the W1, W2, and B that give y hat with the least error. And in the last week, you learned a lot about minimizing functions, including methods like gradient descent. So as you can imagine, this is what we're going to use next. We're going to use gradient descent to minimize L, the loss, and thus find the best W1, W2, and B. And that implies we found the best model for the dataset. So now we know what the problem is. We want to find the prediction function with the best weights and bias that minimizes the loss function L, y hat. So in other words, we want to find the best model that makes the smallest mistakes. Now, how do we find these optimal values? We're going to minimize L using gradient descent. So we're going to find the best W1, W2, and B using gradient descent, and recall that the gradient descent formula updates W1 this way in order to minimize L. Recall that alpha is the learning rate, and then this is how it updates W2, and this is how it updates B. So in other words, you have some W1, W2, and B, some starting values, and then all you need to do is calculate these 3 gradients, and you can update them and get new W1, W2, and B that are better, that are better model, because it has a smaller loss function. And if you do this for a long time, you can imagine that you're going to end up with pretty good weights that have a very low loss function, and that implies a good model. So now I'm going to tell you how to calculate these derivatives. There's going to be a lot of chain rule. So on the left, we have the functions for reference, and on the right, I'm going to calculate the partial derivatives. So first of all, what is di L over di B? Well, take a look at L. L depends on the variable y hat. So we need to do die L over die y hat, and then y hat depends on B. So die y hat over die B. This is nothing more than the chain rule that we learned last week. And the same thing happens for die L over die W1. L depends on y hat, so we have die L over die y hat, and y hat depends on W1, so times die y hat over die W1. And the same thing for die L over die W2. Die L over die y hat, as L depends on y hat, times die y hat over die W2. So now we know what we have to do, and all we have to do is calculate these four derivatives, because notice that die L over die y hat repeats 3 times. So we need to calculate that one, and then the 3 partial derivatives of y hat with respect to W1, W2, and B. And these are much easier than actually plugging in the whole thing. So it's kind of like breaking the problem into easier subproblems. So let's calculate each one of these separately. Let's start with die L over die hat. This is the derivative we have to calculate with respect to y hat. So using the chain rule, this is 1/2 times something squared, and its derivative is the something, y minus y hat. But we still need something more, because we have to take the derivative of the inside with respect to y hat. And the derivative of y minus y hat with respect to y hat is simply -1. So we have that -1 over there. So the first derivative is simply negative y minus y hat. We could write it as negative y plus y hat, but we're going to keep it like this because it's going to make math easier later. Now let's move to the other 3, which are much easier actually. What's die y hat by die b? Well, notice that this is a constant with respect to b. It has nothing to do with b. So really, it's going to be 1 because it's the derivative of the remaining, which is b, by die b. So that's a 1. What about the next one? Die y hat over die w1. Well, notice that this part is a constant with respect to w1. So this may as well be w1x1 plus 7. And its derivative is simply x1, which is the constant that accompanies w1. And similarly, die y hat over die w2, this part's a constant, so it's just x2, the constant accompanying w2. So now that we have these ones, let's plug them back in. I'm going to put them here on the right as reference. And now let's remember the chain rules we already calculated. Die L over die B is die L over die y hat, which is minus y hat, times die y hat over die B, which is 1. So that's the first derivative. For the second one, die L over die W1, it's the usual minus y hat, which is die L over die y hat, times die y hat over die W1, which is x1. And for the final one, die L over die W2, it's going to be the usual die L over die y hat, negative y hat, times die y hat over die W2, which is x2. So these are our 3 derivatives. Now let's go back and remember our main goal. Recall that the main goal was to find the optimal values of W1, W2, and B that give us the predictions y hat with the smallest possible error. And we're going to use the tool that we developed last week, gradient descent. So recall that gradient descent uses these updating formulas to get the new W1. So you start with some W1 and update it as W1 minus learning rate times the derivative of the loss, what we want to minimize with respect to W1. Now what is this? We already calculated it. It's going to be negative x1 times y minus y hat. For W2, again, this is the gradient descent step, and we know this derivative. We already calculated it. We get this. And for B, B is going to be updated as B minus alpha die L over die B, which gets calculated as minus y hat. So this is the gradient descent step. And so if we do this many times, we'll get some really good weights W1, W2, and B that are going to have a really small error and therefore a really good model. You've already seen how to use perceptrons as linear regression problems, but a perceptron can also represent a classification problem, in particular, a binary classification problem. All you have to do is change the activation function. In this video, I show you how. So now that you know how to solve the regression problem with a perceptron and with gradient descent, Classification is actually very similar. It only has one little complication, but it's not that bad. So let's look at an example that you've already seen earlier in the class. You meet an alien civilization and you start listening to the way of speaking. So you take note of 4 sentences in their language that are these 4. They only have 2 words in their language, so it's pretty simple. But what you want to do is be able to tell the mood of each sentence. Now, when the alien said the first sentence, you can notice that they were happy. For the second sentence, they were sad. For the third one, they were sad. And for the fourth one, they were happy. So the idea is to be able to infer from new sentences the mood, if they're happy or sad. So we're going to make a model that will predict the mood based on the sentence. Now, since we want numbers, because models take numbers and not words, then we're going to make the following table where the number of times the word ack and the number of times the word beep are recorded. So the first sentence has 3 times the word ack and 0 times the word beep. So it's 30. For the second one is 02. For the third one is 13. And for the fourth one is 21. So that's the data set for the sentiment analysis classification problem that we're going to solve in this lesson. So the first thing we do is plot the points. So here are the points. And as you can see, the happy points tends to be on the bottom right and the sad points on the top left. So that's probably what the model is going to tell us. But let's turn it into a perceptron. So for the perceptron, we have our inputs labeled x1 and x2, and x1 is the number of times the word ack appears, and x2 is the number of times beep appears. And again, this is going to go through a prediction function just like before with a summation and a bias, etc. And the prediction y hat is going to tell us if the model thinks the sentence is happy or sad. Now, what goes in the center node of the highlighted in red indicates the placement of this line that's going to classify different sentences as happy or sad based on the number of times a particular word appears. This sentence is the one that divides the happy zone in the bottom right from the sad zone in the top left. So let's explore this center node more carefully and the entire classification perceptron further. It's going to be very similar to the regression perceptron, but with a little addition. So again, we're going to have weights W1 and W2 that determine how important any of the features are. Say the word ack is really correlated with happiness, then W1 is going to be a large number. If beep is very irrelevant, then W2 is going to be a small number. However, if beep happens to be inversely correlated with happiness, say it's a very sad word, then W2 is going to be a negative weight. And again, we're going to have a bias input B. So what's going to happen inside the node? We are going to have a summation. So the summations again are going to be x1w1 plus x2w2. So the features times the weights added plus the bias B. So that's just like before. And this produces a continuous number. That's going to be called set. And as I said, that's a continuous number that could be anywhere in the number line. This number could be minus 1,000,000, it could be plus 7,000, it could be 0, it could be 1, it could be whatever. However, that's not the output we want. That's the output we wanted in regression because we wanted any number to be the price. But now we want a number between 1 and 0 because we wanted to tell if it's happy, that's a 1, or if it's sad, that's a 0. So how do we turn the entire number line into the numbers 1, 0, or at least some number in between 1, 0? We're going to use what's called the activation function, denoted by the letter sigmoid of z. And the activation function is actually very useful. It's going to take all the numbers in the number line and crunch them into the interval 0, 1. Now you can still get numbers in between 0, 1. That's okay. If you get a 0.5, it could be that the model doesn't know if the sentence is happy or sad. If you get 0.9, means the model thinks that the sentence is happy. If you get 0.01, then it means that the model thinks the sentence is pretty sad. So the sigmoid function is a huge component of this perceptron. Now let me explore the sigmoid function a little more in detail. The sigmoid function is given by the formula 1 over 1 plus e to the z. And that's going to give us a number between 0 and 1. So in the next video, we're going to get into the sigmoid function in more detail. But for now, just know that it's a very important piece of the perceptron, and the summation in the left gets passed through the sigmoid function in order for our output to be something between 0 and 1, which is exactly what our data set is asking for. So in the previous video, you learned the sigmoid function and how it's super useful in machine learning. And the reason is because it takes the entire number line and crunches it into the interval 0, 1, which is what we want for the output. The formula is 1 over 1 plus e to the minus z. And here is the graph. The graph is this one over here. And notice that the input is the number line and the output is the interval 0, 1. So the input is the horizontal axis and the output is the vertical axis. Notice that it has asymptotes at 0 and 1, which means it never really touches the numbers 0 and 1. But every number has an output strictly between 0 and 1. And for example, sigmoid of 0 is 1/2, because if you plug in a 0 and 1 over 1 plus e to the minus 0, you get 1 over 1 plus 1, which is 1/2. If a number is very, very large positive, like 1,000, then sigmoid of 1,000 is very, very close to 1. And if it's a very large negative number, like minus 1,000, then sigmoid of minus 1,000 is very, very close to 0. However, the sigmoid function has a very, very nice property other than the fact that it crunches the entire number line into the interval 0, 1, and is that its derivative is really nice. So now we're going to calculate the derivative. And why is it important that it's a nice derivative? Because in machine learning, we're going to use derivatives a lot. So it's very important that a function is easy to differentiate. So let's take the derivative in great detail. Sigmoid of z is 1 over 1 plus e to the negative z, which can be written like this. 1 plus e to the negative z to the negative 1. Now we're going to take the derivative of this. So we're going to use the chain rule. For the chain rule, we have d over dz of something to the minus 1 is minus 1 times something to the minus 2. And then we take the derivative of the something inside. That's exactly chain rule. So let's rewrite it as negative 1, 1 plus e to the negative z to the negative 2 times, now d over dz of 1 plus e to the negative z is d over z of 1 plus d over the z of e to the negative z. And that's going to be rewritten as 0 because the derivative of a constant, that's 1, is 0. And here we have the derivative of e to the negative z, which is e to the negative z derivative of negative z by the chain rule. And that last part is going to be minus 1. So we're about halfway there. Notice that this negative 1 gets cancelled with this negative 1, and we have 1 plus e to the negative z to the negative 2 times e to the negative z, which is this. Now this can be rewritten even nicer. Let's write it as e to the negative z over 1 plus e to the negative z squared. And so this is where we are. Now, notice that we can add and subtract 1. Why do we want to add and subtract 1? You'll see. But let's write it like this. And now let's split it as the first 1 plus e to the negative z over the denominator minus 1 over the denominator. Now this cancels with one of these two, and we get 1 over 1 plus e to the negative z minus 1 over 1 plus e to the negative z squared. And that can be written as this minus 1 over 1 plus e to the negative z times itself. And now we're just going to factor the 1 over 1 plus e to the negative z times 1 minus 1 over 1 plus e to the negative z. And why do we want to do that? Well, recall that this is exactly the sigmoid. So the first term is sigmoid, and the second term is 1 minus sigmoid. So isn't that beautiful? The derivative of sigmoid is sigmoid times 1 minus sigmoid. And the fact that this derivative is so easy to calculate means that it's going to be really useful in machine learning. So now that you know all there is to know about the sigmoid function, let's go back to the perceptron. Let's take, for example, the sentence ack beep 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 as an example. This one has the word ack 1 time, so x1 is 1, and the word beep 3 times, so x2 is 3. And let's say that we're in the middle of training the algorithm and the weight that we have are 4.5 for W1, 1.5 for W2, and the bias of 2. So what the perceptron does is it takes these inputs, multiplies them by the weight functions, and applies the sum and then the sigmoid function in order to get a prediction y hat. And the idea is that we're going to use y hat together with a loss function that tells us how far y hat is from what it should be in order to update the weights. So let's say that y is 0, so the sentence is sad. Then we're going to use that to update W1, W2, and B. So basically, we're going to measure how far y hat is from y, and that's the error. Now you may think y hat minus y works really well, y hat minus y squared, or 1/2 times y hat minus y squared, all the error functions we've seen before. Those work. But for classification, the one that works best is called the log loss. So next, I'm going to show you how the log loss is calculated. Log loss is going to be called now L of y hat, and we're going to use that error to update the 3 weights and bring the error down. So let's recap. We have a prediction function y hat with an activation of sigmoid that is applied on the summation coming out of the perceptron, and we have a loss function that is the log loss. Now the log loss is something you've already seen before. Do you remember that example we saw in the previous section where we were trying to find the ideal coin to be able to fit some data set? It was a coin that you need to flip 10 times and you needed to obtain heads 7 times and tails 3 times. And you need to find the perfect coin for that. And the perfect coin was obtained by minimizing some loss function with a logarithm. It's precisely this. So this is actually the loss function for this problem. And you can see that if y is 0, then this is small when y hat is small and large when y hat is large. And if y is 1, then the opposite happens. When y hat is close to 1, this function is small, and when y hat is close to 0, this function is large. In other words, this L of y hat is a large number if y and y hat are far away from each other, and small number if they are close to each other. And there are many reasons why we want to use log loss for this function. One is that the math works out really nicely, but the other one is that this function has a probabilistic nature to it. And the reason is the same reason that it came out of that example with the coins. And classification problems are highly probabilistic because you can think of the output y hat as a probability. Let's say that y hat is 80% or 0.8. That means that the model gives the sentence an 80% probability of being happy. So let's go back to the main goal. The main goal is to find the perfect weights W1, W2, and B that will give us y hat with the least amount of log loss LY hat error. So in order to be able to do this, we need to go back to gradient descent. Recall the gradient descent formula that updates the weights W1 as the old W1 minus a learning rate times the derivative of the log loss with respect to W1, and W2 as W2 minus learning rate times derivative of log loss by W2, and the same thing for B. Bias equals bias minus alpha derivative of log loss by derivative of B. Now, in order to start the algorithm, we simply start with some arbitrary values for the weights and biases, and we're going to start the descent process. So we start with random variables, then we calculate the partial derivatives, and then we update. So in the next video, I'm going to show you how to find these partial derivatives, and you're going to see that the sigmoid and the log loss actually conspire really nicely to get some very nice derivatives. So now we know what the problem is at hand. We want to calculate all those derivatives and be able to do a gradient descent step in order to find the best weights and bias for our dataset. Now, let's focus on weight W1 for a moment. And the idea is to reduce the function LY hat by moving around with W1. So let's first see how W1 affects L. Because if we can find in which direction to move W1 in order to reduce L by a little bit, all we need to do is iterate this step with all the weights many times. So now there are a lot of variables in between L and W1, and one of them is y hat, because y hat is affected by y hat affects L. So we need to find the partial derivative of L with respect to y hat. Now, y hat is affected by W1, so we need to find the partial derivative of y hat by W1. And finally, that tells us how much L is affected by W1. And the missing piece is the partial derivative of L with respect to W1. That's the one we really want to find. Why? Because that one's the one that tells us how much W1 affects L and in what directions. This one is calculated using chain rule. Di L by di W1 is di L by di y hat times di y hat by di W1. So all we have to do is calculate these two in order to calculate di L by di W1. And the same thing happens with W2. We want to change W2 around to reduce the loss, and we have this hidden variable y hat in between, and we want to know how much y hat influences the loss. And we also want to know that how much W2 influences y hat. And therefore, we'll be able to find this derivative over here, di L by di W2, which is calculated using the chain rule just like before. And the same thing happens with B. So reduce the loss function. We use di L by di y hat, which we've already calculated. This one's influenced by B, so di y hat by di B. And that tells us the derivative of L with respect to B. To find this one, again, with the usual chain rule. So we have a lot of derivatives to calculate, and I'm going to put them over here. The first one is di L by di B, which we write using the chain rule, then di L by di W1, and di L by di W2. So we only have 4 things to calculate because di L by di y hat is there many times. So what are these ones? Well, let's recall that y hat is obtained as the sigmoid function of the summation obtained inside W1x1 plus W2x2 plus B, and that the log loss is this function over here. So let's start calculating things. First, let's do di L by di y hat, the one that appears most often. Notice that the logarithm of y hat has as derivative 1 over y hat, and negative y is simply a constant with respect to y hat. So the first term is minus y divided by y hat. And at the end, this is what we're going to have. And the reason is because the second one has a very similar derivative. 1 minus y over 1 minus y hat, because that 1 minus y hat in the denominator comes from logarithm of 1 minus y hat. So when we expand this, these two cancel out, and we get negative 1 minus y hat over y hat times 1 minus y hat. So that's dl by dy hat. We're going to use this one a lot. Now let's calculate the other 3. So how do we calculate that y hat by di W1? Well, remember that the derivative of sigmoid is sigmoid times 1 minus sigmoid. So this is going to be sigmoid of the inner part times 1 minus sigmoid of the inner part, which is the same as y hat times 1 minus y hat, times x1, which is the derivative of the inside by W1. And for the same reason, di y hat by di W2 is this, and di y hat by di B is y hat times 1 minus y hat. So recall that this is using the fact that the derivative of sigmoid of something is sigmoid times 1 minus sigmoid. That's where the y hat times 1 minus y hat come in. So now we've calculated a bunch of derivatives. All we need to do is multiply them. So what's di L by di B? Well, it's di L by di y hat, which is this, times di y hat by di B, which is this. And the same thing we do for di L by di W1. It's di L by di y hat times di y hat by di W1. And finally, the same thing goes for W2. It's the usual one, di L by di y hat times di y hat by di W2. And now we need to cancel out a bunch of things. Notice that this two cancel out. The y hat 1 minus y hat cancel out on the denominator and the numerator. So we end up with some really nice derivatives. Check it out. Di L by di B is simply negative y minus y hat. Di L by di W1 is negative y minus y hat times x1. And di L by di W2 is negative y minus y hat times x2. Notice that if y and y hat are very close, these derivatives are very small, which means you don't need to make a lot of changes because you already have a good prediction. But if you have a bad prediction, y and y hat are really far away from each other. And therefore, you need a large derivative to move things around a lot. And let's go back to where we were. Our main goal was to find the optimal values for W1, W2, and the bias B. So we can use the partial derivative expression we found in our gradient descent expressions as follows. So here's set, here is sigmoid of set, and the output is something between 1 and 0. And the log loss was L of y, y hat. So in order to find the optimal values for W1, W2, and B, we're going to use, you guessed it, gradient descent. And this is the updating step for W1. Now notice that we already know the partial derivative of L with respect to W1, and it's exactly this. And this is the similar step for W2. We can also replace the derivative by what we already found out. And this is the step for replacing B. And again, we can put what we know to be the derivative. So in other words, this is the updating step. You start with some W1, W2, and B, and then you iterate using this procedure. And if you do this many times, you're going to get to some pretty good W1, W2, and B values that will give you a really good model that will map your data set pretty well. So that is gradient descent for a classification perceptron. Now that you know what a perceptron is, you're just one step from knowing what a neural network is. A neural network is just a bunch of perceptrons organized in layers, where the information of these perceptrons is passed to the next layer. And how to train these neural networks? Using gradient descent just like before, except now we have many derivatives. We have to take the derivative of the log loss with respect to each one of the weights and biases of the neural network. Let me show you how. So remember in the previous lesson you worked a binary classification problem where you had to do sentiment analysis. You use this perceptron shown here where Z was the summation of the previous variables time multiplied by the weights, and then sigmoid set was the activation function that got you to find the prediction y hat. Now, turns out that these models are pretty simple and they can only do so well. If you remember, what this thing does is it builds a linear boundary, a line between the happy and sad sentence. But maybe language is much more complicated than that. Maybe it needs boundaries that are much more complex and not just a line. So for that, we use not just one perceptron, but several perceptrons put together. So that's called a neural network. So here we have one perceptron, the red perceptron on top, and then we put a green perceptron on the bottom. And now we have two perceptrons that perhaps do different things. And what do we do with the outputs of these two perceptrons? We plug them into another perceptron, the purple perceptron. And that is a neural network. Now you can imagine that a very complex neural networks will have many perceptrons plugged into others, and the outputs of those are plugged into others, and then you have many layers, and you'll be able to solve very complex problems. For now, we're going to do it with two layers, the one of the red, green, and the purple one, so that we can actually handle the math properly. So here is the math. We're going to have weights, and here we're going to have weights W11, W21, and the bias B1 that goes into the red perceptron. And the sum, as usual, is Z1. And then you apply sigmoid Z1, and you're going to call that A1. So A1 is what comes out of the red perceptron. Now what comes out of the green perceptron? Similar thing. W12 are the weights, W22, the bias is B2, Z2 is the usual summation of the weights times the features plus the bias, and when you apply sigmoid to this, you get A2. And A1 and A2 are the inputs to the purple perceptron. So the weights here are W1 and W2, and then z is obtained as a1w1 plus a2w2, and then you obtain z, and you apply the sigmoid function to this to obtain y hat. So this is a neural network of depth 2 that has one input layer over here, one hidden layer over here, and the output layer. But as I said, you can imagine neural networks with lots and lots and lots of inputs. However, there's one thing missing, right? Perceptrons normally have a bias, and the purple perceptron doesn't have a bias. That's no problem. We'll just put the bias here, and we'll call the bias weight B. And now we have a full neural network. Let's study the inner workings of the red node in our hidden layer. So, focusing on this node alone, we've established that A1, its output, is given by the sigmoid of Z1, and Z1 is given by the usual combination of weights and inputs and the bias. So X1W11 plus X2W21 plus B1. The same thing happens with the green perceptron. A2 is given as sigmoid of Z2, where Z2 is the usual summation of the weights times the features plus the bias. And now let's go to the purple perceptron. For the purple perceptron, the output is y hat and its sigmoid of Z. And Z is, again, the summation of A1W1 plus A2W2 plus B. So the new inputs to the purple perceptron are the outputs of the green and red perceptron, so A1 and A2. And that gets multiplied by the weights W1 and W2, and B gets added to that. And that is the output of the neural network. And as a reminder, here are all the variables. So here's a full picture of the neural network with the inner working and the math behind each one of the nodes. And now, since we're dealing with a classification problem, let's not forget that the error function is the log loss that we saw in our earlier problem to help us measure the error. That is L y hat equals negative logarithm of y hat minus 1 minus y hat logarithm of 1 minus y hat, where y hat is the prediction and y is the target in the training data that we want to hit. So now that we know how a neural network works, let's get to training them. So now that we know how a neural network looks like, all we have to do is find these derivatives in order to do gradient descent. So recall that the goal is to adjust each one of the highlighted weights and bias in order to reduce the loss function L y hat. And so basically, we need to see how each one of these weights affects the loss. And that is what the partial derivative of L with respect to Wij tells us. Same thing with these biases. How do these biases affect the loss? Well, di L over di Bi tells us that. Now, how do the weights W1 and W2 affect the loss? With this partial derivative. And how does this bias affect the loss? With this partial derivative. In other words, these partial derivatives tell us exactly in what direction to move each one of the weights and biases in order to reduce the loss. So that's exactly what we're going to do. We're going to calculate each one of these in order to reduce the log loss function. So let's simplify and only look at these ones over here. Di L over di W11, W21, and B1. And let's also look at di L over di W1 and di L over di B. So let's recall that the way we calculated the output of the red node was, first we did set 1 is this summation, then we applied sigma to get A1, and then we did the summation of the inputs A1 and A2 times the weights W1 and W2 and the bias B, and we applied sigmoid to this set to get y hat. And then with y hat, we found the log loss of y hat. So there's a lot of variables in between L and W11, and we're just going to keep track of all of them to do a humongous chain rule. So in order to reduce this log loss, we need di L over di y hat, and the reason is because L, the loss, depends on y hat. Now y hat depends on z, so we need this derivative too. di y hat over di z. Now z depends on a1, so we need di z over di a1. And a1 depends on z1, so we need di a1 over di z1. Now z1 depends on w11, so we need di z1 over di w11. That's a huge chain rule. This is how it looks. Di L over di w11, which is the one we wanted to find, is equal to di z1 over di w11 times di a1 over di z1 times di z over di a1 times di y hat over di z times di L over di y hat. The product of all this is a really long chain rule, but that's what gives us di L over di 11, the one that we really want. Now let's calculate each one of these separately. What's di L over di w11? Well, this one's easy because it's di z1 over di w11 is the one over here. Each one of these terms is actually really easy. What is this derivative? Well, it's simply x1 because w11 is the variable, x1 is a constant accompanying it, and everything else is a constant, so it has derivative 0. Now let's move to di a1 over di z1. That one is easy too because it's a sigmoid, and the derivative of sigmoid is sigmoid times 1 minus sigmoid, so this is a1 times 1 minus a1. Now, what is di z over di a1? Again, this is a linear equation, so w1 is the derivative. And what's di y hat over di z? This is again a sigmoid, so it's y hat times 1 minus y hat. And finally, what's di L over di y hat? That's the harder one, but we've already calculated this one plenty of times. So our derivative di L over di w11 is the product of all these things. These two cancel out, and so we get this expression over here. So in order to find the optimal value of w11 that gives the least error, we perform gradient descent with this formula. And what's di L over di w11? It's simply this over here. So that is how we change w11. And as you can imagine, that's how you change any wij. You just have to change the subscripts here. But I'll tell you how to do it in a minute. But for the sake of redundancy and to really nail this down, let's do the bias. So in order to reduce this, again, we're going to go a little faster. We need di L over di y hat, and that depends on z, which in turn depends on a1, which in turn depends on z1, which in turn depends on b1. So the long chain rule is this one over here. Product of all these derivatives is equal to di L over di b1. So let's calculate each one of these separately and quickly because we've already done it before for most of them. What's di L over di b1 is the product of di z1 over di b1, which now it's easy, it's 1. Why is it 1? Because b1 is the only variable here, so this may as well be b1 plus some constant. And the derivative of that with respect to b1 is simply 1. And the rest, we already know. This is the sigmoid function. This is a linear function. This is again the sigmoid function. And this one we've already calculated before. So things cancel out. And the way we update b is in order to find the optimal value of b1, then we perform gradient descent with this. Di L over di b1 we've calculated already, and it's this. So let me summarize. The way we update w11 is like this. For w12, it's slightly different. For b1, it's this. And then for the other three weights and biases, it's this. So in short, if you do these updates for a learning rate alpha, you get better weights and biases. So that's how you update the first layer of the neural network. Now let's update the second layer, but this one's much easier because we have to keep track of less things. So here is how you do it. You want to minimize Ly hat. So you want to actually decrease it. dl over dy hat is the first derivative that you need because L depends on y hat. Y hat depends on z. Z depends on w1. And therefore you need this chain rule over here in order to calculate di L over di w1. And let's calculate each one of these separately again. So what's di L over di w1? It's this derivative over here, which is a linear function, so it's a1. This one over here is a sigmoid, so the derivative is y hat times 1 minus y hat. And this one over here we calculated already, so things cancel out and we get something very simple. That to find the optimal value of W1, you perform gradient descent with this formula over here, and since you've already calculated a derivative, you get this. This is how you update W1. I'm going to rewrite it like this by turning a double negative into a positive, and this is how you update W2, and this is how you update the bias. So in short, we've seen how to update each one of the weights and bias of the neural network. So when we do this, we actually get a much better set of weights and biases. And that's how you train a neural network. So now that you know how to calculate the derivative of the log loss with respect to all the weights and biases of the neural network, I'm going to show you how to use this and gradient descent to train your neural network. So let's start building our bigger neural network. This one is going to have 3 layers. An input layer with inputs x1 and x2. Then it's going to have a first layer with some perceptrons and a bias. And then these feed into a second layer with more perceptrons and a bias. And these will feed into a final output layer from which a output of y hat's gonna come out. Now we need to find some notation for the weights. So let's add a superscript of 1 for the first layer. And these ones will feed into summations Z1 superscript 1 and Z2 superscript 1. So everything with superscript 1 is in the first layer. And now these are the A's that are obtained after the sigmoid. Any weight and bias of the second layer is going to have a superscript 2, as well as the sets and the A's, which are obtained by applying sigmoid on the sets. And finally, anything on the third layer is going to have a superscript of 3. And you can imagine that if I continue adding layers, we're going to keep having superscripts of 4, 5, 6, etc. And so that's a pretty consistent notation for all the weights in a neural network. And as usual, L of y hat is the log loss function given by this formula, and that's the one we want to minimize. So now for the purpose of this network, let's clean up the neural network as bit, and let's actually only worry about a few of the weights. And by symmetry, everything's going to be worked out the same for the other weights. So we're only going to care about these ones over here. And so the goal of backpropagation is the method that we're going to use to train neural networks, and it's just going to consist on calculating a lot of derivatives using chain rule and using them to update our gradient descent step just like before, except that now we have to keep track of more variables. So as usual, here is the log loss, and we have to see how the log loss changes with respect to all these weights. And I'm only circling a few of them. It's really a bunch of them, but everything can get calculated using these green ones over here. So what do we need to calculate? We need to calculate di L over di y hat and all the di L over di anything else, because that's what tells us how to move each one of the weights. So let's go to this part of the neural network, the part of the end. And as usual, we need to build a chain because we need this derivative over here, di L over di W superscript 3, and that's going to be obtained as the product of these 3, because that's the chain of command. That's the chain of variables that are in between W superscript 3 and L. So once we calculate these ones, we can do the exact same thing for the bias. So these ones we know how to calculate. Now let's move a little further, and it's the same thing. We need to calculate di L by di W superscript 2, and these are all the variables that are in between. So we need to do a long chain rule of variables, each one depending on the previous one. But as usual, these are either linear functions of sigma or sigmoids, so they're all easy to calculate. And the same thing happens for di L over di B superscript 2. It's just a chain of variables, and we need to multiply them in order to get the chain rule. Now these over here have already been calculated, so we don't need to calculate it anymore. So there's a lot of reuse of variables. So we can just store them over here and continue calculating new ones. Otherwise, we would have to recalculate many things. So it's good to store the ones we've already calculated. And finally, for die L over die W superscript 2, we just have the product of all of these ones over here that can be already calculated from before in our repository of already calculated derivatives times some new ones over here. And as usual, these are easily calculated. So basically, there's a lot of work involved here, but you know what the basic steps are. The basic steps are long chain rule and calculating each derivative separately, and these neural networks are built in such a way that each derivative of the simple ones is either a sigmoid or a linear function, so they're very easy to calculate. The good news is, if you're a machine learning practitioner, you don't need to actually do this. There's some great packages that do it very well. But my philosophy, I always like to see it done carefully at least once, and then you can use the packages and do things very fast. In this and the following videos, I'm going to show you an alternate method to gradient descent called Newton's method. Newton's method is also very fast and very powerful. In principle, Newton's method is used to find the zeros of a function. However, we can adapt it a bit to be used for optimization. Newton's method works in many variables as well. But let's start by looking at how it works in one variable. So let's say you have this function over here, and your goal is to find the zero. So find this point over here. That's the point where f of x is equal to 0. So here's a pretty good method to approximate this zero really well that works similar to gradient descent. Let's start with some random point x0. That's not the zero of the function, but that's okay. We're going to get a better one from here. Let's take the tangent at this point. So let's take the derivative and draw the tangent and see where it hits the horizontal x-axis. And at this point, we're going to call it x1. Notice that x1 is much closer to the 0 than x0. So all we need to do is iterate over here. So let's do it one more time. Draw the derivative and find the new point x2. Notice how close x2 is from the 0 of the function. So we pretty much almost got there. By the third point, we're very, very, very close to the 0. So we pretty much found it. We didn't exactly found it, but we got pretty close. And that's the point, to be able to approximate the 0 of the function really well. Now let's add some numbers. This line over here has slope f prime of x0. And this height over here is f of x0. And the base is x0 minus x1. So this formula over here for the slope is rise over run. Now rise is f of x0 and run is x0 minus x1. So therefore f prime of x0 is f of x0 divided by x0 minus x1. We can manipulate this to get that x1 is equal to x0 minus f of x0 divided by f prime of x0. And that's the iterative step. You have f0, you simply calculate x1 based on x0 and then iterate. So how do we iterate? Well, let's go to one more step. Let's say that you've done it k times and you got to xk. This slope over here is f prime of xk. This height is f of xk. And this horizontal distance is xk minus xk plus 1. Therefore, doing the same math as before, xk plus 1 is equal to xk minus f of xk divided by f prime of xk. And since you know xk, you know f, and you know the derivative, then you can find xk plus 1. So you iterate on this step and you get Newton's method. Now the question is, how do you use that for optimization? Because remember, gradient descent found the minimum of a function. Newton's method is only finding the 0 of a function, not the minimum. Well, we simply remember that when you want to minimize a function g of x, you actually have to find the zeros of g prime of x. So if I can find the zeros of a function, I'm very close to minimizing it. I just have to look at all the zeros and see which ones are minimum, because those are the candidates for minimum. So in other words, if I let f of x be the derivative of g of x, then by finding the zeros of f of x, I am minimizing g prime of x. And the derivative of f prime of x is simply the derivative of g of x and the derivative of that. So in other words, here are the algorithms. For Newton's method, you start with some x0. Now, if I wanted to find the zero of f, what I have to do is update, and the step is xk plus 1 is xk minus f of xk over f prime of xk, where xk is my kth iteration and xk plus 1 is my k plus 1th iteration. Now in Newton's method for optimization, I have to do the same thing, except not with f, but with g prime. So I have xk plus 1, the k plus 1th iteration is xk minus g prime of xk divided by g prime of xk prime, the second derivative. So that's going to be a big deal very soon. But before that, let's do the iterative step. The iterative step is repeat 2 until you find the root on the left, and on the right is repeat 2 until you find the minimum. So now that you know Newton's method, let's put it in action. I want to recall this function you saw in week 2 when you learned about gradient descent. The function was e to the x minus logarithm of x, and its derivative was e to the x minus 1 over x. Recall that the minimum for this function was the omega constant 0.5671, etc. And so let's approximate this minimum. Recall that in order to use Newton's method for a minimum, you actually have to use it to find the zeros of the derivative. So we're going to try to find the zero of this function, which is the derivative, e to the x minus 1 over x. Now, what's the derivative of the derivative? Well, if we take the derivative of e to the x is again e to the x, and the derivative of 1 over x is minus 1 over x squared. So the derivative of the derivative is e to the x plus 1 over x squared. That's gonna be our f prime of x when we're taking f of x equals g prime of x. In other words, our new function to find the zero is f of x, and we're gonna use f prime of x to help us with Newton's method. So let's start. Let's do a few iterations. We start with the iteration with the first value x0 equals 0.05. That's the first iteration. Now let's take the derivative and see where it hits the zero. So it's at a point x1, not too far from it. x1 is given by this formula using Newton's method. We evaluate the derivative at e to the 0.05 minus 1 over 0.05. That's the derivative, divided by e to 0.05 plus 1 over 0.05 squared. And we get 0.097. So that's our new point x1. So with x1, we're going to iterate again. We draw the tangent, see where it hits, and that's at a point x2. How do we calculate x2? By plugging in these values. So x2 is going to be 0.183. And again, we take the derivative, see where it hits 0, and that's our point x3. How do we calculate x3? Using the derivative again. And the value for x3 is 0.320. We're getting closer. Let's do it one more time. With x3, we draw the derivative, we see where it hits the axis, and we get x4. And to calculate x4, we use the iterative formula again to get 0.477. Notice how close we're getting. Let's do one more iteration. With x4, we draw the derivative, we see where it hits. That's at a point x5. And x5 is going to be calculated like this, and the value is going to be 0.558. And let's just do one more. We draw the derivative again, we see where it hits, and it's at x6. And at 6 is going to be 0.567. And notice that with only 6 iterations, we actually got really close to the minimum, which is 0.567. Newton's method is actually really fast, and this example shows it. And as you can see, it's just a simple step that we can iterate many times. In the previous video, you learned how the derivative of a derivative can appear naturally in Newton's method. This derivative of a derivative actually has a name, the second derivative. In this video, I'm going to show you the second derivative, some of its properties, and how it can be really useful in optimization problems. So previously, you learned how to use Newton's method for optimization, and remember that this was the iterative step. In order to find the minima or the maxima of the function, you need to find the zeros of the derivative. At some point, you use this thing, the derivative of the derivative. So that's new. That's the second derivative, and it's very, very useful. It gives us a lot of information about the function. In Leibniz notation, that can be written as d squared f over dx squared, or as d by dx up d by dx of f. In Lagrange notation, it's much simpler. If f prime is the derivative, then the second derivative is f prime prime of x. Now, I like to understand things in real life, and remember that to understand the first derivative, we used velocity, because if x is the distance traveled by a car, then v is velocity, and v is the rate of change of distance with respect to time, or dx over dt. Well, in this case, what's the rate of change of velocity with respect to time? It's simply the acceleration. Acceleration is dv by dt, or d squared x over dt squared. Acceleration tells us how much the velocity is changing with respect to time. So if your acceleration is positive, means your velocity is increasing with respect to time. And if the acceleration is negative, means the velocity is decreasing with respect to time. And if you have zero acceleration, means you have constant velocity. So now let's do some plots. Imagine that you're driving your car, and this is the plot. So in the horizontal axis, you have time, and in the vertical axis, you have distance. And let's say that the plot is this one over here. So let's analyze it bit by bit, and let's see how it translates in terms of velocity. So at the start of your trip, your car is stopped, and you need to start it and increase your velocity until you reach a constant speed. So the slope keeps getting bigger as time goes by. Now, imagine that this piece of function can be modeled as 750t squared. And let's say that this behavior goes on for 2 minutes, or 2 over 60 hours. Now, the derivatives for these first minutes is the line 1500t. Why? Because the derivative of 750t squared is 1500t. Now let's say that for the next couple of minutes you keep going at a steady pace. So you have the same rate of change. Now let's say that this can be modeled by the equation 50t minus 5 over 6. That's a line. It's a linear equation. Now, since the distance is linear, then you reach a constant velocity of 50 kilometers per hour. Why? Because the derivative of 50t minus 5 over 6 with respect to t is simply 50. Now let's say that you keep going for 5 minutes until you realize that you forgot your wallet at home and you actually need to go back. So at this point, you start pressing the brakes, and the brakes make you slow down until you stop. And when you stop, you have a derivative of 0. And notice that you've reached the maximum, because this is as far as you got. After this, you start going back. So you start turning around and going at a negative speed. And now notice that the slope starts positive, but keeps getting smaller and smaller until it reaches 0 at the peak value of the distance. And finally, it gets negative when you start going in the opposite direction. So this one over here is the graph of the speed. You started positive, then you reached 0 when you stopped, and then you started going negative because you started going in the opposite direction as before. Let's say that the expression for the distance was this one, minus 1500t squared plus 300t minus 11.26. So what's the equation for the line? Well, it's the derivative of this, which is 300 minus 3000t. It's a linear equation. Now let's say that after 2 minutes of going back, you finally set at a constant speed until you reach the starting point. So what happens is that over here, you have a constant speed, and let's say the distance function is 55 over 6 minus 50t. Therefore, the velocity is minus 50. So now that we have the graph of velocity based on the graph of distance, let's find the graph of acceleration based on the graph of velocity. So for your first 2 minutes, your speed is a line. That means your derivative is a constant, which is a value 1500. Because you have a constant acceleration, then your speed increases linearly. Now between 2 and 5 minutes, when you travel at constant speed, the acceleration is simply 0. When you travel at constant speed, you're not accelerating. There's no change in velocity. Now between 5 and 7 minutes, your speed is again a line, but now with negative slope, because your deceleration is minus 3000. Or in other words, your acceleration is minus 3000 because you're decelerating. And finally, for the final stretch, you have an acceleration of 0 again, because you're going at a constant speed of minus 50. So when we put the first graph and the third graph together, we go from x to a, from distance all the way to acceleration. And as you can see, for the first 2 minutes, when the distance increases at an increasing rate, you have a positive acceleration. Between 2 and 5 minutes, when you travel at a constant pace, the acceleration is 0. After 6 minutes, you keep going forward, but slower and slower, and between 7 minutes, you're going back. So for these transitions, you experience a negative acceleration. Notice that at the maximum distance traveled, you had a negative acceleration, meaning a negative second derivative. This is very important. And finally, until the end of your trip, your acceleration becomes 0, since you're again going at a steady pace. So as you can see, the second derivative gives a measure of the amount by which a curve deviates from being a straight line. This is called the curvature. Let me get a bit more into the curvature. When you have a positive second derivative, as in the first piece of the distance, you have a concave up function. This is also a convex function. In this function, as you can see, the second derivative is positive and the function is increasing at an increasing rate. You're increasing the speed and therefore your distance increases more and more each time. Over here you have the opposite. Your function is concave down, and that happens when the second derivative is negative. For the other two, the second derivative is 0. For this, it's inconclusive, so you have no curvature. Now let me get a bit more into curvature. This over here is a concave up function. It looks like a happy face. And this one over here, it's a concave down function. It looks like a sad face. And the way to tell is when the second derivative is positive, you have a concave up or convex function. And when the second derivative is negative, you have a concave down function. And how is this useful for optimization? Well, the second derivative tells you if something is a maximum or a minimum. Remember that the points of derivative 0 are the candidates for maximum or minimum, but we don't know if they're maximum or minimum. So the second derivative tells us. Take a look at the first one. This one over here has a derivative of 0 and the second derivative is positive and it's a local minimum. However, this one over here is a local maximum and the second derivative is negative. However, for the other two, it's inconclusive. When the second derivative is 0, we don't know if we're at the presence of a maximum or a minimum. Now, there's something very interesting that happens, and is that the first derivative tells us one thing and the second derivative tells us another thing. When the first derivative is positive, we have an increasing function, and when it's negative, we have a decreasing function. However, when the second derivative is positive, we have concave up, and when the second derivative is negative, we have concave down. And as you can see, when you have a concave up point, the point with derivative 0 is a local minimum, whereas when you have a concave down, the point with the derivative is 0 is a local maximum. In the previous video, you learned the second derivative and how it's useful in optimization problems. That was all in one variable. Next, I'm going to show you how it works in more than one variable. For multiple variables, the second derivative is actually a matrix full of second derivatives called a Hessian. So now I'm going to show you the Hessian, its properties, and how it's used in optimization. In particular, when we want to optimize a function of many variables, we can use multivariable Newton's method, and that one uses a Hessian. So let's start with a little comparison between functions of 1 and 2 variables. So recall that a function of one variable is called f of x, and it only depends on the variable x, whereas a function of two variables depends on variables x and y. So the first derivative is simply f prime of x, which is the rate of change of f with respect to the only variable x. When you have two variables, you have two rates of change. The rate of change of f with respect to x, called fx, and the rate of change of f with respect to y, called fy. And if you put them together, you get the gradient nabla f, which is a vector. Now what happens with the second derivative? Well, you have x prime prime for the second derivative of one variable, that's the rate of change of the rate of change of fx. And for two variables, well, let's see what we're going to have. This is what I'm going to show you in this video. So to understand the second derivative in two variables, let's analyze this simple example. F of xy equals 2x squared plus 3y squared minus xy. We can take the derivative with respect to x, which is 4x minus y, and with respect to y, which is 6y minus x. And now we can take the second derivative, so we can take the derivative with respect to x, which is 4. And we can take the derivative of 4x minus y with respect to y, and that's minus 1. For the second one, 6y minus x, we can take the derivative with respect to x and with respect to y, and we get minus 1 and 6. So these four are the rate of change of the rate of change. So it's the rate of change of fx with respect to x, of fx with respect to y, and then of fy with respect to x, and of fy with respect to y. Notice something peculiar. These two are the same thing. That happens almost all the time. But let's summarize this a little bit. So the first two are the rate of change with respect to x and then with respect to x, and also with respect to y and with respect to y. So these work exactly like in one variable, because pretty much if you have f as a function of only x, you can take f prime prime of x, and the same thing with y. However, the last two are a bit peculiar. That's the change in the slope along one coordinate axis with respect to tiny changes along the orthogonal coordinate axis. And these two are actually the same thing. Actually, this is in most cases. You need both partial derivatives to be differentiable. And when both partial derivatives are differentiable, then the derivative with respect to x of the derivative with respect to y is the same as the derivative with respect to y of the derivative with respect to x. So in Leibniz notation, we can write this as di squared f over di x squared, di squared for di y squared, and for the other two, di squared f for di x di y, and di squared f over di y di x. And Lagrange notation, we get fxx, fyy, fxy, and fyx. So now, let me show you what the Hessian matrix is. Let's go back to this little graph over here where we took the derivative with respect to x and y, and then the partial derivatives with respect to x and y of each one of these. When we put these four together in a matrix, we get the Hessian matrix. So the Hessian matrix here is 4, -1, -1, 6. And the Hessian matrix gives us a lot of information about second derivatives. And it also is very useful in optimization, as we'll see soon. In the general case, we have our function f, the partial derivatives fx and fy, and their partial derivatives fxx, fxy, fyx, and fyy. And when we put these together in a matrix, we get the Hessian matrix, just like before. And as I mentioned before, there's a lot of information in this Hessian matrix. So now let's go back to our table. In our table, we have that the second derivative for one variable is simply f prime prime of x. And what is it in two variables? Well, it's the Hessian. So it's the matrix that keeps track of all the second partial derivatives. So now let me tell you what information does the Hessian bring in terms of optimization. Remember that for functions of one variable, several things can happen. If the second derivative was positive, then you have a function that is concave up, in which case there was a local minimum. If the second derivative was negative, then you had a function that was concave down, and so it would have a local maximum. And the case where the second derivative was E0, then it was inconclusive. You didn't know very much. So the same thing happens for many variables, except you have to keep track of a couple more things. So what does concave up mean in two or more variables? It means it looks like this function, 2x squared plus 3y squared minus xy. Visually, you can tell that the minimum is at this point over here, which corresponds to x equals 0 and y equals 0. So by analogy with the one variable case, this kind of looks like a happy face, right? But can we show it numerically? Well, let's look into the Hessian. And so remember, in one variable, if we wanted to know if it was concave up, we looked at the second derivative and checked if it was positive. But now we have a matrix. How do we check if a matrix is positive or negative? Well, you actually look at the eigenvalues. Let's calculate the eigenvalues. So if you recall from the linear algebra class, the way to calculate them is by taking a look at the equation determinant of Hessian minus lambda I, which is this matrix over here, and the determinant is this, and that is this quadratic. When we find the roots of this quadratic, they are 6.41 and 3.59. Notice that they are both positive. So for a matrix, this is the equivalent of being a positive number. It means the matrix is positive definite. So because all the eigenvalues of this matrix are positive numbers, then the function is concave up and the point 0, 0 is a minimum. Now, let's look at a very similar function. This one is minus 2x squared minus 3y squared minus xy plus 15. This one looks like it has a maximum point here at 0, 0. And now we are going to look at the Hessian matrix. So here is the gradient and here is the Hessian at 0, 0. Now let's look at the eigenvalues of the Hessian. So we're going to solve the same equation as before, the determinant of h minus lambda I. We factor it and we get the eigenvalues minus 3.49 and minus 6.41. Both of them are negative. So that is like saying that the matrix is negative. It's actually called negative definite. And when a matrix has all the eigenvalues negative, then it's concave down, and therefore the point 0, 0 is a maximum. Now, not every matrix has all the eigenvalues positive or all the eigenvalues negative. Something like this can happen, a saddle point. This is the function 2x squared minus 2y squared, which is a saddle point. Looks like a saddle or a potato chip. And over here, well, this point is neither a maximum or a minimum, right? And now let's take a look at the Hessian. So this over here is the gradient, minus 4x minus 4y, and the Hessian at 0, 0 is this matrix over here, 4, 0, 0, minus 4. What are the eigenvalues here? Well, if we solve for the determinant of h minus lambda I equals 0, we get that the eigenvalues are minus 4 and 4. So in this matrix, not all the eigenvalues are positive and not all the eigenvalues are negative. So therefore, it's neither positive definite nor negative definite. And so we cannot conclude anything. In this case, we have that because this eigenvalue is negative and the other one is positive, then 0, 0 is actually a saddle point, a point that is neither a minimum nor a maximum. So here is the summary. We're going to have one variable functions, two variable functions, and functions in n variables. So what happens with a local minimum? In one variable, you have to have a happy face. So f prime prime of x is bigger than 0. And obviously f prime of x has to be 0 for this to happen. In two variables, you have to have an upper paraboloid, like the concave up function you saw in this video. And for that to happen, both eigenvalues have to be positive of the Hessian. And in the general case, you simply have to have a Hessian with n eigenvalues, all of them bigger than 0. And for a local maxima, same thing. You have a sad face in one variable, so the second derivative is negative. For the two-variable case, you have a down paraboloid, like the other function you saw in this video, and both eigenvalues have to be negative. And in the general case, you simply have to have a Hessian with n eigenvalues, all of them less than 0. And for anything else, we need more information. If in one variable case we have that the second derivative is 0, we don't know if it's a local maximum or minimum. It could be either one or none. In the two-variable case, we have a saddle point with one eigenvalue bigger than 0 and one smaller than 0. And in the general case, you simply have that some are positive, some are negative, some are 0, and those cases are inconclusive. So let me repeat. If all of them are strictly positive, you have a local minimum. If all of them are strictly negative, you have a local maximum. If anything else happens, if one of them is 0, or if some of them are positive, some of them are negative, anything like that, then you don't know what you have, at least with this test. Let's conclude this week by learning how to apply Newton's method to optimize functions of many variables. And as you guessed it, the Hessian appears here. So remember that at the beginning of this lesson, we saw Newton's method and found an expression for iteratively finding the minimum or maximum out of a function. For one variable, the update equation has this expression that depended on the current value, the first derivative, and the second derivative. We could just as easily rewrite this like this, where instead of dividing by f prime prime of xk, you multiply by the inverse of f prime prime of xk. Now what happens in two variables? Well, in two variables, you don't have one coordinate, you have two coordinates, x and y. So your kth iteration is xk, yk, and your k plus 1 iteration is xk plus 1, yk plus 1. And how do you obtain the k plus 1 iteration from the kth iteration? Well, let's look at the expression above. This is the second derivative, turns into the Hessian. And this is the first derivative, turns into the gradient. And notice that the second derivative is inverse because you're dividing by it. Well, that simply turns into the inverse of the Hessian matrix. So this is the expression for two variables. And you can see that actually this works for n variables. I simply have to do a vector of n coordinates minus an n by n matrix, the Hessian inverse, times a vector of n coordinates, which is the gradient. Now you have to be very careful. It's tempting to write it like this as well, but this actually won't work. You cannot multiply the gradient at the left of the matrix, you have to multiply at the right. And the reason is that the matrix is 2 by 2 and the vector is 2 by 1, and you cannot multiply a 2 by 1 vector to the left of a matrix, you can only multiply it at the right. So when working with two variables, the orders is pretty crucial. Now, it's a lot of work to actually prove this formula, but we're gonna just take it as is and notice that it actually is a sensible generalization of the one variable case. And now that you know Newton's method for more variables, let's put it in practice. Here is a function that is concave up, and we're gonna try to find the minimum. So first, let's take a look at the two partial derivatives with respect to x and y, and then the partial derivatives of those with respect to x and y, and with respect to x and y. So the Hessian is obtained with these four expressions at the right, and the gradient is formed by the two expressions in the middle. In other words, here's the gradient, and here is the Hessian. So now, using the Hessian and the gradient, you're going to use Newton's method. So let's start at some point. Let's say the point x0, y0 equals 4, 4. Here is the gradient at that point. So what we did is in the expression of the gradient, we simply put the numbers 4 and 4. And now let's find the Hessian. So now notice that this point 4, 4 is not the zero of the function. But we're going to get closer and closer using Newton's method. So what's the first point? Well, the second iteration is going to be 4, 4, the first iteration, minus the Hessian inverse times the vector. And that's actually going to be 2.58, 2.62. And that's the new point. Notice that it's much, much closer to the 0.00, which is the root that we're looking for. Now let's iterate again. So we have that this is the gradient, and that this is the Hessian, and the second iteration is this point minus the Hessian inverse minus the gradient. So we get the point 1.59, 1.67. And let's actually continue repeating it. And when you repeat it many times, you end up in the actual 0. So it takes 8 steps to get this close. Check it out. The 8th iteration is 4.15 times 10 to the minus 17 and minus 2.05 times 10 to the minus 17. This is an awfully small number. It's really, really, really close to 0, 0. And 0, 0 is actually the optimal point you were looking, because that is the root of the function. So as you can see, just like with one variable, Newton's method in 2 variables is a really, really fast method to be able to approximate really closely the 0 of a function.